Have you ever stood outside on a clear, dark night, looked up at the stars, and felt that deep, almost primal sense of wonder? That feeling is one of the oldest and most universal human experiences, a quiet hum of curiosity that has echoed across centuries and civilizations. For thousands of years, we've traced constellations, told stories, and dreamed about what lies beyond our world. Yet even now, with all our advanced technology and knowledge, the cosmos remains the greatest source of mystery we've ever encountered. It's a place where the rules of reality as we know them bend, break, and sometimes disappear entirely, inviting us to question everything we think we understand. Today, we're setting out on an epic journey together, one that will take us to the very edges of understanding and imagination. We're diving deep into the Chronicles of Celestial Wonders, a sweeping exploration of the most profound cosmic mysteries that both captivate and confound the brightest minds on Earth. From the mind-bending properties of black holes, where gravity is so intense that not even light can escape, to the haunting possibility of life hidden in the oceans of distant moons, we'll venture into questions that challenge not just science, but the very nature of existence itself. This isn't just about facts and figures, it's about the stories behind the science, the human passion driving discovery, and the awe that comes from staring into the infinite. What you're about to experience is more than a video, it's an invitation to wonder, to question, and to rediscover that childlike amazement we so often leave behind. Because the universe isn't just something out there, it's part of us. Every atom in our bodies was forged in the heart of a star. Every breath we take is part of a cosmic dance that began billions of years ago. So whether you're a seasoned space enthusiast or someone who's just beginning to look up with curious eyes, you belong here. Settle in, open your mind, and let's embark on this adventure into the grandeur, the mystery, and the breathtaking beauty of the cosmos. What we're really talking about here is not just a list of unsolved puzzles. It's the fundamental architecture of reality itself. These cosmic mysteries act as gateways, inviting us to look beyond what we can see and touch, and to question the very nature of existence. Consider this: over 95% of the universe is made up of substances we cannot see, cannot touch, and do not fully understand. Dark matter and dark energy are the dominant forces shaping the cosmos, yet they remain entirely invisible to our most powerful telescopes and detectors. It's as if we're only perceiving the shadow of the universe, while the real substance lingers just outside our grasp. Scientists often use powerful metaphors to describe these elusive components. Dark matter is like the hidden skeleton of the cosmos, an unseen framework whose gravitational pull holds galaxies together, preventing stars from flying off into the void. Without it, the majestic spiral arms of galaxies and the vast clusters we observe simply wouldn't exist. On the other hand, dark energy behaves in almost the opposite way. It's a repulsive force causing the universe to expand at an accelerating rate, pushing galaxies apart as if space itself is stretching faster and faster. This creates a cosmic tug of war, one force pulling things together, the other driving them apart. Together, they form the dynamic and invisible engine of our universe's evolution. This duality illustrates a humbling truth: the more we learn, the more we realize how much we have yet to discover. For every mystery we solve, two new ones seem to emerge from the shadows. It's not a sign of failure, but a testament to the boundless complexity and beauty of the cosmos. What other invisible forces or undiscovered entities might be influencing the universe right now, beyond the reach of our current technology? The possibility invites a profound sense of wonder, encouraging us to keep exploring, questioning, and reaching for a deeper understanding. But what exactly is this mysterious substance that holds the cosmos together? To understand dark matter, we need to rewind to the 1930s, when a brilliant and unconventional astronomer named Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. By measuring how fast these galaxies were moving, he made a startling calculation. There simply wasn't enough visible mass, the stars and gas we can see, to generate enough gravity to keep the cluster from flying apart. He concluded that some unseen dunkle materie, or dark matter, must be providing the missing gravitational glue. For decades, his idea was largely ignored, but in the 1970s, astronomer Vera Rubin provided undeniable evidence. Her meticulous work on the rotation curves of spiral galaxies showed that stars at the outer edges of galaxies were orbiting just as fast as those near the center, defying the laws of gravity as we knew them. The only logical explanation was that each galaxy was embedded within a massive, invisible halo of matter, a halo that extends far beyond the visible edge of the stars we see. This discovery fundamentally changed our understanding of the universe's composition. We now know that this dark matter isn't just a small component. It's the main ingredient, making up about 85% of all matter in the cosmos. So if we can't see it, what could it possibly be made of? The leading candidates are not made of the protons, neutrons, and electrons that form everything we're familiar with. Instead, physicists are hunting for exotic particles that barely interact with normal matter except through gravity. One prime suspect is the WIMP, or weakly interacting massive particle. These hypothetical particles are thought to be heavy and slow-moving, rarely bumping into ordinary atoms. To find them, scientists have built incredibly sensitive detectors and placed them deep underground, in abandoned mines or beneath mountains, to shield them from the constant cosmic noise on the surface. They wait, hoping to see the tiny telltale flash of heat or light that would signal a WIMP has finally collided with an atom in their detector. Another intriguing candidate is the action, a particle originally proposed to solve a different puzzle in particle physics. Actions would be incredibly light, almost ghost-like, and could theoretically flow through space in vast numbers, collectively creating the gravitational effects we observe. Experiments are also searching for these, using powerful magnetic fields to try and convert these elusive actions into detectable photons. Yet, despite decades of searching with increasingly sophisticated technology, these particles have remained stubbornly hidden. This persistent lack of a direct detection has led some scientists to propose a far more radical idea. Perhaps we're looking for the wrong thing entirely. What if dark matter isn't a particle at all? A minority but respected viewpoint suggests that our theory of gravity itself might be incomplete on the largest scales. This idea, known as modified Newtonian dynamics or MUND, proposes that gravity behaves differently when it becomes extremely weak, like at the edges of galaxies, eliminating the need for any invisible matter. This proposition pushes at the very foundations of physics, challenging Einstein's theory of general relativity, which has been spectacularly successful for a century. It forces us to ask a profound question: is the mystery due to a missing type of matter, or a missing part of our understanding of how gravity works? There are even more exotic theories that venture into the realm of extra dimensions, suggesting that the gravitational influence we attribute to dark matter might be leaking into our universe from other dimensions we cannot perceive. The enigma of dark matter is far more than a missing puzzle piece. It's a glaring sign that our picture of the universe is incomplete. Its resolution won't just tell us what the invisible stuff is, it could completely rewrite the textbooks on physics, revealing new layers of reality we have only just begun to imagine. Just as dark matter's gravitational pull works to hold the cosmos together, a far more mysterious and dominant force is actively working to tear it apart. This force is dark energy, and its discovery in the late 1990s sent shockwaves through the scientific community, completely upending our understanding of the universe's ultimate fate. For decades, astronomers had assumed that the gravitational attraction between all the matter in the universe would be slowly putting the brakes on the expansion that began with the Big Bang. The central question was whether there was enough matter to eventually halt and reverse the expansion in a big crunch, or if the universe would just keep expanding forever at a gradually slowing pace. Two rival teams set out to measure this deceleration by studying distant supernovae, which serve as standard candles for measuring cosmic distances. To their absolute astonishment, they found the opposite. The universe wasn't slowing down at all. It was expanding faster and faster, as if something was pressing down on the cosmic accelerator. This revelation was so profound and unexpected that it earned the leaders of those teams the 2011 Nobel Prize in Physics. It meant that a previously unknown form of energy, now called dark energy, is permeating all of space and counteracting the relentless pull of gravity on the largest scales. A useful way to picture this is to imagine the universe as the surface of a balloon. Galaxies are dots on that balloon. As you inflate it, all the dots move away from each other. Now imagine the balloon starts inflating at an ever-increasing rate. Not only are the dots moving apart, but the spaces between them are growing larger at a speed that is itself increasing over time. That is the unsettling reality of our cosmos, driven by this enigmatic dark energy. So what could possibly be causing this accelerated expansion? The leading candidate is something that Albert Einstein himself proposed, then later called his biggest blunder, the cosmological constant. This is the idea that empty space, or the vacuum, is not truly empty but seething with a constant, underlying energy. According to quantum physics, virtual particles are constantly flickering in and out of existence, and this quantum foam imbues every cubic centimeter of space with a tiny amount of energy. If this vacuum energy is real and positive, it would produce a repulsive force that causes space itself to expand. The enormous problem, however, is that when physicists calculate how strong this vacuum energy should be based on quantum theory, their answer is wrong by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of physics. This staggering discrepancy means we are either completely misunderstanding the quantum vacuum, or dark energy is something else entirely. Other theories suggest that dark energy could be a dynamic field that changes over time, similar to the inflationary field that caused the universe to expand exponentially in its first fraction of a second. Some even more exotic ideas propose that it's a sign of extra dimensions hidden from our perception, or that our laws of gravity break down on the scale of the entire universe. What we do know for certain is that dark energy is the dominant component of our universe, making up about 68% of its total energy budget. This means it single-handedly dictates the long-term fate of everything. If it continues to accelerate expansion as it does now, we are headed for a big freeze or heat death. In this lonely scenario, galaxies will be pushed so far apart that the sky beyond our local group will go completely black. Star formation will cease as gas clouds are ripped apart, and eventually all stars will burn out, leaving the universe a cold, dark, and empty place. The profound nature of dark energy forces us to ask even deeper questions. Is it perfectly uniform across the entire cosmos, or could its strength vary in different regions? If it's not constant, could those variations hint at a far more complex and textured reality? Could its behavior be a clue that we live in a multiverse, one bubble among countless others with different fundamental properties? Every question about dark energy seems to lead to another, more fundamental one about the very fabric of reality. It is a reminder that we are still at the very beginning of a much larger story, one that is still being written as we peer deeper into the expanding darkness. But if dark matter and dark energy represent the invisible scaffolding and engine of the cosmos, then black holes are its most terrifying and awe-inspiring monsters. These are not merely empty voids in space. They are regions where spacetime itself is warped beyond recognition, where gravity becomes so overwhelmingly powerful that nothing, not even light, can escape its clutches once it crosses a point of no return known as the event horizon. The concept was so radical that even Albert Einstein doubted such objects could truly exist in nature. Yet today we have not only confirmed they are real, but we have actually taken their picture. The story of how we came to understand these cosmic beasts begins with the theory of general relativity. Einstein's equations predicted that if a massive amount of matter were compressed into a sufficiently small space, its gravity would become so intense that it would carve a bottomless pit in the fabric of the universe. For decades, these objects were just mathematical curiosities. Then, in the 1960s, physicist John Wheeler poetically named them black holes, and the hunt for real evidence began. The first major breakthrough came in the 1970s with the discovery of Cygnus X1, a powerful source of X-rays in our galaxy. Astronomers realized these intense emissions were coming from superheated gas being ripped from a companion star and spiraling at near light speed into an invisible, incredibly dense object, a black hole. This was the first of many to be found, revealing that black holes are not rare anomalies but common features of our universe. At the very center of a black hole lies its greatest mystery, the singularity. This is a point where all the matter that has ever fallen in is crushed to infinite density, a place where the laws of physics as we know them simply cease to function. Space and time as concepts break down entirely. It's a mathematical error in the heart of reality, a sign that Einstein's theory of gravity, while brilliant, is incomplete. It fails to reconcile with the other pillar of modern physics, quantum mechanics. For decades, it was thought that nothing could ever escape a black hole's grip, that they were eternal prisons. Then Stephen Hawking made a revolutionary calculation. He realized that if you apply quantum theory right at the edge of the event horizon, pairs of virtual particles popping in and out of existence can be separated. One particle falls in while the other escapes into space. This steady trickle of escaping particles, now known as Hawking radiation, means that black holes are not completely black. They slowly, over unimaginable eons, lose mass and evaporate. This discovery created a massive puzzle known as the information paradox. According to quantum mechanics, information, the specific identity of every particle that fell in, can never be truly destroyed. But if a black hole evaporates and disappears, what happens to all that information? Does it vanish forever, violating a fundamental law of the universe, or is it somehow encoded in the Hawking radiation? This paradox pits general relativity against quantum mechanics, and solving it is one of the biggest goals in theoretical physics today, potentially leading us to a long-sought theory of everything. Our understanding leaped from theory to breathtaking reality in April 2019, when the Event Horizon Telescope collaboration released the first ever image of a black hole. This was not a photograph in the traditional sense, but a reconstructed image made by combining data from radio telescopes across the globe, effectively creating a planet-sized observatory. The target was a supermassive black hole at the heart of the galaxy Messier 87, a behemoth weighing in at 6.5 billion times the mass of our Sun. The image showed exactly what Einstein's equations had predicted a century earlier: a dark central shadow, the event horizon, surrounded by a brilliant, lopsided ring of light. This ring is the accretion disk, superheated gas and dust swirling at relativistic speeds, its asymmetry caused by the mind-bending effects of the black hole's spin. More recently, we've seen the image of Sagittarius A, the much closer but quieter supermassive black hole at the center of our own Milky Way galaxy. These images are more than just confirmations. They are tools that allow us to test the limits of physics under the most extreme conditions imaginable. This leads us to the most speculative and fascinating questions of all. What truly lies beyond the event horizon? Some theories suggest that a black hole could be a tunnel, a wormhole connecting two distant points in spacetime, or even bridging to a completely different universe. Others propose the idea of a firewall of intense energy that would incinerate anything falling in, though this remains highly controversial. The reality is that we simply do not know, and we may never know, for the interior of a black hole is the ultimate secret keeper. It forever hides its truths from the outside universe, challenging our intellect and inviting us to dream of realities beyond our own. Now, with all these cosmic wonders unfolding around us, from the invisible grip of dark matter to the mind-bending nature of black holes, it's almost impossible not to look up at the stars and ask one of the most profound and deeply human questions of all: is anybody else out there? The numbers alone suggest the answer should be a resounding yes. Our Milky Way galaxy is home to hundreds of billions of stars, and we now know that a significant fraction of them host planets. Many of these exoplanets orbit within their star's habitable zone, that sweet spot where temperatures could allow for liquid water, a key ingredient for life as we understand it. With such an unimaginably vast number of potential homes for life, the cosmos should be absolutely teeming with activity. The universe has had over 13 billion years to get the party started, more than enough time for intelligent civilizations to arise, flourish, and perhaps even begin to explore the galaxy. This simple, logical expectation makes the reality we observe all the more startling. When we point our most powerful telescopes and listening dishes at the heavens, we are met with a profound and puzzling silence. Where is everybody? This glaring contradiction between the high probability of extraterrestrial life and the complete lack of any evidence for it is known as the Fermi Paradox, named after the physicist Enrico Fermi. The story goes that during a casual lunch conversation in the 1950s about flying saucers and the potential for interstellar travel, Fermi simply asked, "But where is everybody?" His point was blunt and brilliant. If spacefaring civilizations are even remotely possible, the age of the universe suggests the Earth should have been visited, or at the very least colonized long ago. The fact that we see no artifacts, no obvious engineering projects on a stellar scale, and hear no signals in the void, presents a mystery that is both thrilling and deeply unsettling. Scientists and thinkers have proposed a wide range of potential solutions to this great silence. One of the most sobering is the idea of a great filter. This theory suggests that the evolution of life from its basic origins to a spacefaring, communicative civilization requires overcoming a series of incredibly difficult challenges. The Great Filter is a hypothetical barrier, a step in this long chain of events that is so improbable that it prevents almost all life from progressing beyond it. The terrifying question is, where is this filter located? Is it behind us? Perhaps the jump from simple prokaryotic cells to complex eukaryotic life was a fantastically rare fluke, meaning the universe might be filled with simple bacteria, but is almost entirely devoid of complex animals or intelligence. Or, even more chillingly, is the Great Filter still ahead of us? This would mean that the step we are currently approaching, the development of a global, technological civilization, almost always leads to self-destruction, whether through nuclear war, environmental collapse, or some unforeseen technology that proves to be our undoing. If this is the case, the eerie silence of the cosmos is a grave warning, a preview of a universe littered with the ghosts of civilizations that ultimately failed to survive their own adolescence. Other explanations are less apocalyptic but equally fascinating. The Zoo hypothesis proposes that advanced alien civilizations are indeed out there and are fully aware of us, but they have chosen to deliberately avoid contact, placing Earth in a kind of cosmic wildlife preserve. They might be observing us from a distance, allowing humanity to develop naturally without interference, perhaps until we reach a certain level of maturity or wisdom. Another idea is that the universe is just too big. The vast distances between stars and the limitations of the speed of light could mean that signals or probes from other civilizations simply haven't had enough time to reach us, or vice versa. We might be like isolated islands in an immense ocean, unaware of the others simply because the waves that could carry a message take millions of years to cross the gulf. Or perhaps we are looking for the wrong things. Our primary method of searching, through radio telescopes listening for deliberate signals, might be as primitive as trying to spot an airplane by waiting for someone on board to light a signal fire. An advanced civilization might have moved on to a technology for communication that is completely unrecognizable to us, like neutrino beams or quantum entanglement, leaving our searchers effectively deaf to their conversations. For over 60 years, the search for extraterrestrial intelligence, or SETI, has been systematically scanning the skies, listening for any faint whisper that stands out against the natural radio background noise of the universe. Initiatives have grown more powerful and sophisticated, like the Breakthrough Listen project, which is using some of the world's largest telescopes to conduct the most comprehensive search ever undertaken. They've examined millions of stars and analyzed countless radio channels, and while there have been a few intriguing anomalies like the famous WOW signal detected in 1977, a strong, narrow-band radio burst that lasted for 72 seconds and has never been explained or repeated, the result has largely been the same: silence. This ongoing lack of a confirmed detection forces a kind of cosmic introspection. It asks us to consider not just where the aliens are, but who we are. Are we a cosmic accident, a one-in-a-trillion fluke of nature, alone in the immense darkness with no one to talk to? Or are we simply young, latecomers to a galactic community whose conversations are happening on a channel we have not yet learned to tune into? This mystery ultimately ties into the very core of our search for meaning and connection in the universe, a quest that now leads us to examine other, more recent and equally bizarre signals that do reach us from the depths of space. While the silence in the hunt for extraterrestrial intelligence is profound, the universe is far from quiet. In fact, it occasionally screams. Scattered across the cosmos are incredibly powerful, fleeting signals that have jolted astronomers awake to a whole new celestial phenomenon. These are fast radio bursts, or FRB, and they represent one of the most electrifying and perplexing mysteries in modern astrophysics. Imagine a flash of radio light so intense that it outshines entire galaxies, but one that lasts for less time than it takes to blink your eye. That's the essence of an FRB, a blast of energy that packs a staggering punch and then vanishes without a trace, leaving behind more questions than answers. The story of their discovery reads like a classic scientific detective tale. The first known FRB was found not in real time, but by sifting through old data. In 2007, a young graduate student named Duncan Lorimer was analyzing archival observations from the Parkes Radio Telescope in Australia, searching for new pulsars. Buried in the data from 6 years earlier was something that didn't fit any known pattern. A single, colossal burst of radio waves that had arrived on August 24, 2001. It was a spike of energy so powerful and so brief that it was dismissed by some as terrestrial interference, perhaps a microwave oven being opened prematurely at the observatory. But its dispersion measure, a telltale sign of how much material the signal had traveled through, indicated it had come from far beyond our galaxy, from a distance of billions of light years. This was no kitchen appliance. This was a message from the deep cosmos, written in a language we did not yet understand. Since that first, lonely burst, the field has exploded. Advanced instruments like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have turned detecting FRBs into almost a daily occurrence. This telescope, which looks like a series of half-pipes from a sprawling skate park, is uniquely designed to scan huge swaths of the sky simultaneously. It has now catalogued hundreds of these events, painting a picture of a universe that is crackling with these energetic pops. Some FRBs are one-off events, a single, brilliant shout into the void. Others are repeaters, firing off multiple bursts from the same location at irregular and unpredictable intervals. This distinction is crucial, as it strongly suggests there are at least two different types of sources capable of producing these incredible flashes. The sheer energy involved is what truly bends the mind. A typical fast radio burst can release more energy in 1,000th of a second than our sun puts out over several decades. Whatever is causing these events is harnessing and releasing power on an almost unimaginable scale. So, what cosmic engine could possibly be responsible for such a violent and efficient outburst? The leading natural suspect is a type of neutron star called a magnetar. These are the remnants of supernova explosions, but they are born spinning incredibly fast and possess magnetic fields that are trillions of times stronger than Earth. It's thought that a starquake on the surface of a magnetar, a sudden cracking of its ultra-dense crust, could release a titanic shockwave of energy, funneled by the immense magnetic field into a brilliant beam of radio waves that we see as a fleeting burst. In 2020, a magnetar within our own galaxy actually emitted a burst of radio energy that, while not as strong as a typical extragalactic FRB, provided the first tantalizing direct evidence linking these objects to the phenomenon. But magnetars are not the only potential culprit. Other theories involve cataclysmic collisions, such as two neutron stars merging or a neutron star being consumed by a black hole. These extreme events could, in their final, violent moments, produce a similar brilliant flash. And then, of course, there is the more speculative possibility that cannot be entirely ignored. Could some FRBs, particularly the repeating ones, be evidence of advanced technology? The idea of using focused beams of energy for interstellar propulsion, like a light sail pushed by a powerful laser, has been seriously proposed by scientists. A burst of radio waves of the exact kind we see could be a side effect of such an immense engineering project, an unintentional beacon announcing a civilization's activities across the vastness of intergalactic space. While this is considered a far less likely explanation, the sheer mystery of FRBs means all plausible ideas remain on the table. What makes these signals more than just a curiosity is their incredible utility. As an FRB travels across millions or billions of light years, its different frequencies are slowed down by the tenuous gas between galaxies ever so slightly. By measuring this delay, astronomers can use FRBs as the most precise tools to weigh the missing ordinary matter in the universe, the atoms that are predicted to exist but have been incredibly difficult to detect. They are illuminating the cosmic web itself, the vast, invisible structure that connects all galaxies. So, while we hunt for their origin, FRBs are already helping us map the architecture of the cosmos, proving that even our greatest mysteries can become our most valuable tools. And to truly understand the extreme physics that might be behind them, we must now turn our attention to the factories that create such incredible forces, the dense, spinning corpses of dead stars known as neutron stars. To comprehend the staggering reality of a neutron star, you must first witness the death of a giant. When a massive star, many times larger than our Sun, exhausts its nuclear fuel, its life ends not with a whimper, but with a cataclysm of almost unimaginable violence. The star's core, no longer supported by the outward pressure of fusion, collapses under its own immense gravity in a fraction of a second. The outer layers are blasted away in a supernova explosion so brilliant it can outshine an entire galaxy, while the core is compressed into an object of almost pure, mind-bending density. What remains is a neutron star, a cosmic tombstone just 10 to 15 miles across, yet containing more mass than our entire Sun. The numbers are so extreme they defy everyday understanding. Imagine taking all the people on Earth and compressing them into a single sugar cube. That density is the normal state of matter in the heart of a neutron star. A single teaspoon of this material wouldn't just be heavy, it would weigh billions of tons, a mass equivalent to a mountain range held in the palm of your hand. This incredible density is the key to their nature. The collapse is so forceful that it overwhelms the structure of atoms themselves. Electrons are literally crushed into protons, merging to form neutrons and neutrinos. The entire star becomes a giant atomic nucleus, a city-sized ball of neutrons packed shoulder to shoulder, held together by the strongest force in the universe. The surface gravity is so intense that if you were to drop a marshmallow onto it from just a meter away, it would hit with the energy of 1,000 hydrogen bombs. It is a place where the rules of physics are pushed to their absolute limit, creating states of matter that simply cannot be replicated in any laboratory on Earth. Scientists refer to neutron stars as their ultimate laboratory, a natural testing ground for how matter behaves under conditions of pressure and density so extreme that the very particles were made of breakdown and surrender to new, exotic rules. While all neutron stars are born from this same violent process, some reveal themselves to us in a truly spectacular way. These are the pulsars, the cosmic lighthouses that turned a theoretical curiosity into an observable and incredibly useful reality. A pulsar is simply a rapidly spinning neutron star with a powerful magnetic field that isn't aligned with its rotation axis. This misalignment acts like a colossal generator, accelerating charged particles along the magnetic field lines out of the star's magnetic poles. This creates two intense, narrow beams of radiation radio waves, light, X-rays that shoot out into space. And because the magnetic axis is tilted as the star spins, these beams sweep across the cosmos like the beacon of a lighthouse. If Earth happens to lie in the path of that sweeping beam, we see a perfectly regular pulse of energy with every rotation. The timing of these pulses is astonishingly precise. Some pulsars rotate hundreds of times per second, and their periods are so stable they rival atomic clocks. This precision makes them invaluable tools for astronomers. They've been used to test Einstein's theory of general relativity with exquisite accuracy, to probe the thin gas between the stars, and even as navigation beacons for proposed interstellar travel, providing a cosmic GPS for the galaxy. But even these paragons of cosmic regularity sometimes hiccup. Astronomers have observed events known as glitches, where a pulsar's rotation suddenly speeds up by a tiny but measurable amount. These glitches are like a subtle, deep secret being whispered from within the star. The leading explanation is that they provide a window into the star's mysterious interior. The crust of a neutron star is thought to be a rigid, crystalline lattice of atomic nuclei, while the inner core may be a superfluid, a frictionless state of matter where neutrons flow without any resistance. This superfluid rotates at a constant speed. Occasionally, the rigid outer crust, which is slowly slowing down due to its energy loss from radiation, may suddenly become coupled to this faster spinning superfluid interior, causing the whole crust to jerk forward in a glitch. Other theories suggest these events could be tiny starquakes, where the incredibly dense crust fractures and settles, changing the star's moment of inertia and causing its spin to change. Each glitch is a precious data point, helping us map the bizarre layers of a world where a teaspoon of matter could outweigh a mountain. The greatest mystery, however, lies at the very heart of a neutron star. As we peer inward in our models, the pressure and density become so astronomically high that we enter the realm of pure speculation. We know that at a certain point, the neutrons themselves might not survive. They could break down into their constituent parts, quarks. This could create a quark star, a hypothetical object even denser than a neutron star, where matter exists as a soup of free floating quarks. Going even further, some theories suggest that strange quarks, a heavier type of quark, could become the dominant particle, forming a strange star. This strange matter could be the most stable form of matter in the universe, meaning that every neutron star might actually be a strange star in disguise, and that such matter could be infectious, converting any normal matter it touches. While this remains speculative, it highlights a profound truth. By studying these distant, extreme objects, we are not just learning about stars, we are probing the fundamental building blocks of reality itself, uncovering secrets that we could never hope to find confined here on Earth. For over a century, the idea of gravitational waves was a quiet prediction in the margins of Einstein's theory of general relativity, a mathematical curiosity that even he doubted we would ever be able to detect. The concept is both simple and profound. Just as a moving boat creates ripples on the surface of a pond, any object with mass that accelerates through the fabric of spacetime should, according to Einstein, generate ripples in that fabric itself. These ripples are gravitational waves, stretching and squeezing space itself as they travel outward at the speed of light. But the catch is that they are incredibly, almost impossibly, faint. The waves passing through you right now from distant cosmic events warp the space you occupy by a scale far smaller than the nucleus of an atom. Detecting such a minuscule signal seemed like science fiction, a task of literally astronomical precision. That all changed on September 14, 2015. After decades of design, construction, and painstaking upgrades, the twin observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO, were finally online and sensitive enough to listen for the universe's faintest whispers. On that morning, they heard a cosmic shout. A signal lasting less than 0.2 of a second swept through both detectors, separated by 3,000 miles with a time delay that matched the speed of light. The waveform was a perfect chirp, a rising frequency and amplitude that exactly matched what Einstein's equations predicted for the final, frantic moments of two massive black holes spiraling into each other. This event, dubbed GW150914, was a collision that occurred 1.3 billion years ago, releasing more power in gravitational waves than all the stars in the observable universe combined for that brief instant. For the first time in history, we had directly observed the vibrations of spacetime itself, confirming a key piece of general relativity and opening an entirely new sense with which to perceive the cosmos. This breakthrough was not just a confirmation, it was the dawn of an entirely new field of astronomy. Before this, all of our knowledge of the universe came from studying light, from radio waves to visible light to gamma rays. Gravitational waves are fundamentally different. They are not made of photons, they are a distortion of the stage upon which everything plays out. This allows them to travel through the universe almost completely unimpeded, carrying with them a pristine, unaltered record of the most violent and energetic events. By reading these ripples, we can essentially hear the universe. The first signal told us the masses of the two black holes, about 29 and 36 times the mass of our Sun, and revealed that their merger created a single, spinning black hole of 62 solar masses, with the remaining 3 solar masses converted directly into energy and radiated away as gravitational waves. This was a direct observation of a process that was completely invisible to telescopes, a secret the universe had held onto for over 1 billion years. The true power of this new sense, however, is realized when we combine it with our old ones. This is the era of multi-messenger astronomy, where we observe cosmic events through multiple channels simultaneously. The most spectacular example of this came on August 17, 2017. LIGO, along with its European counterpart Virgo, detected the gravitational wave signal of 2 neutron stars colliding. Crucially, the signal was long, lasting about 100 seconds, and its location in the sky was pinpointed with unprecedented accuracy. Within moments, observatories around the world and in space were alerted and swiveled to look at that patch of sky. They were rewarded with an incredible light show. They saw a kilonova, a brilliant flash of light 1,000 times brighter than a typical nova, whose color shifted from blue to red over several days. This event was the cosmic forge that scientists had long hypothesized. The violent collision of these ultra-dense stellar corpses blasted out material that rapidly formed heavy elements like gold, platinum, and uranium. In that one observation, we learned that the gold in a wedding ring or the uranium in a power plant was likely born in the spectacular collision of 2 dead stars, witnessed by us over 100 million years later. As our detectors become even more sensitive, and as new observatories join the network in space, we are poised to listen to a much wider symphony of gravitational waves. What else might be out there creating these space-time ripples? Theorists have a long list of potential sources that could revolutionize our understanding of physics. We could detect the faint hum from the merging of supermassive black holes at the centers of galaxies, events so powerful they would send waves that LIGO can't see, but which future space-based detectors like LISA will be designed to hear. There's the tantalizing possibility of cosmic strings, hypothetical, incredibly thin defects in the fabric of spacetime left over from the Big Bang, which, if they exist and vibrate, would create a unique gravitational wave signature. We might even detect the faint rumble from primordial black holes, which could have formed in the chaotic first moments of the universe, and might even make up a portion of the elusive dark matter. Each new chirp, each new ripple detected, is like tuning into a new channel on a cosmic radio. We are no longer just stargazers. We are now listening to the very vibrations of the universe, hearing the collisions of black holes, the mergers of neutron stars, and perhaps one day the echoes of the Big Bang itself. This new window allows us to probe the most extreme gravity in the universe, testing Einstein's theory in regimes where it might finally break down and pointing us toward a deeper, more complete theory of gravity. It is a direct line to the most secret and powerful events in the cosmos, guiding our search for understanding all the way back to the very beginning of everything. But to truly understand the universe's origin story, we need to rewind the cosmic clock all the way back to time zero. The prevailing scientific narrative for how everything began is the Big Bang Theory, a model that describes the universe's birth from a state of almost unimaginable heat and density approximately 13.8 billion years ago. Picture all the matter and energy that now makes up hundreds of billions of galaxies, each with hundreds of billions of stars, compressed into a space trillions of times smaller than a single atom. This was the primordial singularity, a point where the known laws of physics simply break down, and concepts like space and time as we understand them cease to have any meaning. From this initial state, the universe began to expand and cool, allowing the fundamental forces to separate and the first particles to condense out of the seething energy. Within the first 3 minutes, the first atomic nuclei, hydrogen and helium, were forged in the furnace of the early cosmos, setting the stage for everything that was to come. While the Big Bang framework is incredibly successful, it presented cosmologists with a few deeply puzzling problems. Why does the universe appear so remarkably uniform in all directions? When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, the temperature is the same everywhere to within 1 part in 100,000, even in regions of space that, given the universe's age, should never have been in contact with each other. This is known as the horizon problem. Furthermore, the geometry of the universe appears to be perfectly flat, a delicate balance between the density of matter and the rate of expansion that seems like an astonishingly unlikely coincidence. These puzzles demanded a solution, and in the early 1980s, a physicist named Alan Guth provided a revolutionary one: the theory of cosmic inflation. Inflation proposes that a fraction of a second after the Big Bang, the universe underwent a breathtakingly brief period of exponential expansion, inflating from a subatomic speck to something roughly the size of a grapefruit in less than a trillionth of a trillionth of a trillionth of a second. This incredible growth spurt would have stretched the fabric of spacetime itself, smoothing out any initial wrinkles or irregularities, explaining the observed uniformity and flatness. Just as importantly, inflation provides the origin of all structure. The quantum fluctuations that were present at that tiny scale, tiny, random variations in energy, would have been stretched to enormous sizes by the inflationary expansion. These minute ripples in spacetime became the gravitational seeds around which all future cosmic structure would form. The vast cosmic web of galaxies and galaxy clusters we see today is a direct result of these quantum seeds, magnified across the entire universe. Our strongest evidence for this entire cosmic saga comes from the cosmic microwave background, or CMB. This is the oldest light we can see, a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for electrons and protons to combine into neutral atoms, allowing light to travel freely for the first time. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and most recently the Planck mission, have mapped this faint radiation with exquisite precision. The tiny temperature variations they detected in the CMB, the hot and cold spots that differ by mere millionths of a degree, match the predictions of inflationary theory perfectly. They represent the blueprint for the universe, the imprinted signature of those initial quantum fluctuations that would, over billions of years, gravitationally collapse to form every galaxy, star, and planet. Yet for all its success, inflation raises profound new questions of its own. What was the mysterious field, often called the inflaton field, that drove this explosive expansion? What mechanism triggered it to turn on, and more puzzlingly, what caused it to turn off? The theory works beautifully, but the underlying physics of the inflaton remains one of the biggest unsolved problems in cosmology. Furthermore, some anomalies in the CMB data continue to intrigue and challenge scientists. Perhaps the most famous is the cold spot, a large, unusually cool region in the sky that appears to be difficult to explain by the standard model of inflation alone. Some have speculated, though it remains highly speculative, that it could be evidence of a collision with another universe, a bruise on our cosmos from a long ago impact with a separate bubble universe in a vast multiverse. This idea leads us to one of the most mind-bending implications of some inflationary models, the multiverse. If inflation can happen once, the theory suggests it can happen again, an eternal process creating a vast, perhaps infinite, ensemble of universes beyond our own. Each of these bubble universes could have different physical constants, different dimensions, and even different laws of physics. In this breathtaking scenario, our universe is not the entire show but merely one page in an infinite cosmic library. While the multiverse remains a highly controversial and philosophical concept, critics argue it is untestable and therefore not proper science. It is a direct, and for some, an unsettling prediction of the mathematics behind our best theory of the beginning. All of this brings us back to the most fundamental and haunting question of all. What came before the Big Bang? What was the source of the initial singularity? The frustrating truth is that our current physics hits a wall at this point. The equations of general relativity break down at such extreme energies and densities. To answer this, we need a theory of quantum gravity, a way to unite the large-scale world of gravity with the tiny quantum realm. Until we have that final theory, the question of what, if anything, preceded our universe or how something could emerge from what appears to be nothing remains the ultimate mystery. Our journey to the beginning of time doesn't provide a final answer, but instead reveals a new frontier, one that challenges our very definitions of existence and nothingness, and prepares us to ask why this particular universe seems so perfectly arranged for life to exist. This uncanny precision in the very fabric of reality is what scientists call the fine-tuning of the universe. It's the startling realization that the fundamental numbers governing physics seem to have been set to incredibly specific values, and if any one of them were even slightly different, life as we know it would be utterly impossible. It's as if the cosmos was constructed with a very specific set of blueprints, and the margin for error was vanishingly small. Consider the force of gravity. If the gravitational constant were just a tiny bit stronger, stars would burn through their fuel at a ferocious rate, collapsing into black holes long before life could ever evolve on any orbiting planets. If it were slightly weaker, matter would never have clumped together to form stars and galaxies in the first place, leaving the universe a cold, thin, and eternal haze of hydrogen gas. The universe would be stillborn, devoid of any structure or complexity. This delicate balance extends to the very heart of matter itself. The mass of a proton is almost, but not quite, identical to the mass of a neutron. That minuscule difference is absolutely critical. If it were reversed, protons would be unstable and decay into neutrons, meaning atoms could never form. There would be no chemistry, no molecules, and certainly no us. Even the strength of the force that holds atomic nuclei together, the strong nuclear force, is set on a razor's edge. If it were just a few % weaker, simple hydrogen would be the only element in existence, as protons could never overcome their mutual repulsion to stick together and form heavier elements like carbon or oxygen. A universe without carbon is a universe without the complex chemistry essential for life. On the other hand, if the strong force were slightly stronger, all the hydrogen in the early universe would have fused into heavier elements almost instantly. Without the long, stable burning of hydrogen in stars, there would be no sustained energy source to power living worlds. The universe is not just habitable, it appears to be perfectly calibrated for habitability. This profound observation leads us directly to the anthropic principle, a concept that is as fascinating as it is controversial. In its simplest form, the principle states that the universe must have the properties we observe because if it didn't, we wouldn't be here to observe it. It's a kind of cosmic selection bias. We shouldn't be surprised to find ourselves in a universe compatible with our existence, because we couldn't possibly find ourselves in one that isn't. While this might sound like a tautology, it forces a serious scientific and philosophical conversation about why this particular universe is so accommodating. Does our existence itself explain the fine-tuning, or does it merely describe it? This is where the explanations diverge dramatically, each one taking us down a different path of understanding our place in the cosmos. One of the most popular scientific explanations is the multiverse theory. This idea suggests that our universe is not the only one, but is just one bubble in a vast, perhaps infinite, cosmic foam of universes. In this breathtaking scenario, each universe is born with its own random set of physical constants and laws. The vast majority of these universes would be stillborn or sterile, their numbers set to values that prevent any complexity from ever arising. But in a few, by pure statistical chance, the numbers line up just right. We, of course, find ourselves in one of those rare, life-permitting universes simply because we couldn't exist anywhere else. In this view, there is no fine-tuner, there is just an immense lottery, and we hold the winning ticket. The challenge with this idea is its testability. If other universes are forever beyond our observational reach, does the multiverse remain in the realm of philosophy rather than science? Some physicists suggest that clues might be found in the cosmic microwave background or in the detailed properties of the Higgs boson, offering a potential, though distant, path to evidence. Other perspectives venture beyond pure chance. Some argue that fine-tuning points toward a deeper, underlying law of nature that we have not yet discovered, a theory that would naturally explain why these constants have the values they do, making life not a lucky accident but an inevitable outcome of the physics. Another, far older explanation is that of intentional design, a viewpoint that sees the universe's parameters as evidence of a purposeful creator. While this idea sits outside the boundaries of natural science, it remains a powerful interpretation for many. Ultimately, the mystery of fine-tuning doesn't force a single answer, but it does force a profound question about meaning. It asks us to consider whether we are the unlikely product of a boundless cosmic accident, or if we are participants in a universe that is, in some deep and fundamental way, meant to be known. This search for a universe that is not just habitable but actually inhabited is what drives our next great quest, the hunt for other worlds that might also hold the spark of life. The hunt for other Earths has moved from the realm of science fiction into a vibrant, data-rich field of modern astronomy, fundamentally reshaping our understanding of planetary systems and the potential for life. For centuries, we could only wonder if other stars were accompanied by worlds of their own. Today, we know the answer is a resounding yes. The number of confirmed exoplanets now climbs into the thousands, with statistical estimates suggesting our galaxy alone could be home to more planets than stars. This isn't just a census of distant rocks, It's the first step in a grand cosmic survey to determine if we are alone. The most thrilling discoveries are those planets found orbiting within their star's habitable zone, that Goldilocks region where conditions are just right, not too hot and not too cold, for liquid water to potentially exist on the surface. Water, as the essential solvent for all life as we know it, becomes our guiding beacon in this immense search. Among these tantalizing targets, a few names stand out as prime candidates for future investigation. Proxima Centauri b is a rocky world, roughly Earth-sized, orbiting the closest star to our own Sun, a mere 4.2 light-years away. Then there's the TRAPPIST-1 system, a compact family of 7 Earth-sized planets orbiting a cool, tiny red dwarf star 39 light-years from Earth. Several of these worlds, particularly TRAPPIST-1e, orbit snugly within the habitable zone. These aren't just dots on a chart. They represent our best, most accessible opportunities to peer into the atmospheres of other worlds and sniff out the chemical signs of life. This is the new frontier, and it's being led by a revolutionary observatory, the James Webb Space Telescope. With its unparalleled infrared sensitivity, Webb acts as a cosmic chemist, capable of dissecting the faint starlight that filters through an exoplanet's atmosphere during a transit. It can search for the telltale spectral fingerprints of potential biosignatures, gases like oxygen, which on Earth is largely produced by life, or methane, which can have biological origins. Detecting such an imbalance, a chemistry that seems out of equilibrium, could be our first hint that we are not alone. However, simply residing in the habitable zone is no guarantee of a garden paradise. Astronomers have come to realize that true planetary habitability is a far more complex and delicate equation. A planet's distance from its star is just the opening line of a much longer story. Consider the star itself. Many promising exoplanets, like those in the TRAPPIST-1 system, orbit red dwarfs. These stars are far more temperamental than our stable Sun. They are prone to violent flares of ultraviolet radiation that could strip away a planet's atmosphere and bathe its surface in sterilizing radiation, unless that planet has a strong magnetic field to act as a protective shield. This highlights another critical factor: a planet's interior. A molten core that generates a protective magnetosphere is vital for deflecting stellar winds. Furthermore, geological activity driven by internal heat is likely crucial for recycling nutrients and regulating atmospheric gases through processes like volcanism and plate tectonics. A geologically dead world may be a biologically dead world. This complexity leads us to worlds that defy our Earth-centric imagination. Our solar system has two basic types of planets: small, rocky worlds like Earth and Mars, and large gas giants like Jupiter and Neptune. But in the exoplanet catalog, we find a bewildering array of in-between worlds that have no direct counterpart here. Super-Earths are rocky planets several times more massive than our own, with crushing surface gravities that could create bizarre, high-pressure forms of matter. Mini-Neptunes are gaseous planets smaller than our Neptune but larger than Earth, likely possessing deep, global oceans beneath thick, hydrogen-rich atmospheres, not oceans of water, but perhaps supercritical fluids with properties unlike anything on Earth. Could life emerge in such an alien ocean, under immense pressure and in total darkness? The discovery of extremophiles on Earth, organisms thriving in boiling hydrothermal vents, in acidic lakes, or buried deep under Antarctic ice, tells us that life is incredibly tenacious and adaptable. It forces us to broaden our definition of habitable and consider that the most common abodes for life in the galaxy might be these dark, watery worlds, not the sun-drenched, Earth-like twins we've long envisioned. This incredible diversity of exoplanets expands the playing field for life exponentially. It suggests that the ingredients and conditions for life might be scattered far more widely throughout the cosmos than we ever dared hope. But with this expansion comes a deeper, more fundamental question. If the conditions are right, how does life actually begin? The presence of a habitable world is one thing, but the spark that ignites the transition from chemistry to biology is another mystery entirely. This pushes our inquiry beyond the search for homes and toward the very origins of the living process itself. The question of how life first sparked into existence is arguably the most profound mystery we face, a puzzle that sits at the intersection of astronomy, chemistry, biology, and even philosophy. We see life teeming all around us on Earth, a beautiful and complex tapestry of organisms, but its very origin remains shrouded in the deep past, an event lost to time some 4 billion years ago. Unraveling this mystery does more than just satisfy our curiosity about our own beginnings. It fundamentally shapes how we search for life beyond our world. If we understand how life starts, we can better predict where else we might find it. The scientific pursuit of life's origin is known as abiogenesis, the idea that life arose naturally from non-living matter through a series of gradual chemical steps on the early Earth. Our planet's infancy was a dramatically different place, with a hostile atmosphere lacking oxygen but rich in gases like methane, ammonia, and water vapor. In this primordial soup, the first building blocks of life had to somehow assemble themselves. One of the most famous experiments to test this idea was conducted in the 1950s by Stanley Miller and Harold Urey. They sought to recreate these early conditions in a lab, sealing those simple gases in a glass apparatus and subjecting them to electrical sparks to simulate lightning. Astonishingly, within just a week, the once clear water had turned a murky brown, and analysis revealed it was rich in amino acids, the fundamental components of proteins which are essential for life as we know it. This groundbreaking work showed that the ingredients for life could form readily under prebiotic conditions. However, creating amino acids is a far cry from creating a living cell. This is where the mystery deepens considerably. The leap from a collection of organic molecules to a self-replicating, metabolizing system is a chasm that scientists are still struggling to bridge. How did these molecules organize themselves? How did they develop a way to store information and pass it on? One compelling theory points to the deep ocean floor, to hydrothermal vents. These are not the scorching black smokers, but cooler alkaline vents that produce porous, rocky structures full of tiny compartments. These natural chambers could have acted as the first cells, concentrating the simple organic molecules and providing a gradient of chemical energy that could power primitive metabolic reactions. Within these rocky crucibles, the gap between chemistry and biology might have begun to close. Another fascinating possibility suggests that we might be looking for the answer not just on Earth, but across the solar system. This is the concept of panspermia, the idea that the seeds of life, or at least its fundamental building blocks, are common throughout space and can be transported from one world to another by hitchhiking on comets, asteroids, or meteorites. We know that impacts can launch rocky debris from a planet's surface into space, and that some hardy microorganisms, like certain bacteria, can enter a dormant state and potentially survive the harsh conditions of space travel. We have even found complex organic molecules, including amino acids, on meteorites that have landed on Earth. This raises the provocative notion that life on Earth may not have originated here at all, but could have been delivered from Mars or elsewhere, a cosmic seedling that found fertile ground on our young planet. If true, it would mean life could be a shared feature of many worlds, all potentially sharing a common ancestry that dates back to before the planets themselves were fully formed. The discovery of extremophiles here on Earth has given tremendous weight to the idea that life is not a fragile fluke, but an incredibly robust and tenacious force. These are organisms that thrive in environments we once thought were utterly uninhabitable, in the superheated water boiling out of deep-sea vents, in the acidic runoff from mines buried under kilometers of Antarctic ice, or in rocks deep within the Earth's crust. Their existence dramatically expands our definition of a habitable zone. It tells us that life can persist in conditions of extreme temperature, pressure, acidity, and radiation. If life can find a way in these punishing niches on our own planet, then why could it not also gain a foothold in the subsurface ocean of a distant, icy moon, or in the damp clay layers beneath the rust-colored surface of Mars? The resilience of life suggests that once it gets started, it is remarkably difficult to eradicate, and it can adapt to a stunningly wide range of environments. So, are we the product of an incredibly rare and lucky series of accidents, a statistical miracle in a universe that is largely sterile? Or is life a common, almost inevitable outcome of cosmic chemistry, an emergent property of matter and energy under the right conditions? The answer to this question will redefine our place in the cosmos. If life is a cosmic imperative, then the universe could be teeming with it, and our search is not for a needle in a haystack, but for one tree in a vast forest. This line of thinking naturally pulls our gaze away from distant stars for a moment and back into our own celestial neighborhood, to the most promising places right next door where this universal spark might also have caught flame. The search for life beyond Earth has dramatically shifted from gazing at distant stars to focusing on enigmatic, frozen worlds right here in our own solar system. For generations, we imagined aliens on planets orbiting other suns, but some of the most promising habitats for life are actually the moons of giant planets, hidden beneath shells of ice that have protected vast, dark oceans for billions of years. Jupiter's moon Europa and Saturn's moon Enceladus have completely rewritten the textbook on where life could exist. These are not the cold, dead lumps of rock we once thought they were. They are dynamic ocean worlds, and they may be the best chance we have of discovering that we are not alone. The engine that makes this possible is a subtle but powerful force known as tidal heating. As these moons orbit their massive parent planets, they are not following a perfect circular path. They are constantly being stretched and squeezed by the immense gravitational pull of Jupiter and Saturn. This perpetual gravitational flexing generates immense heat deep within their cores, much like repeatedly bending a metal coat hanger back and forth will make it warm to the touch. This internal furnace is so effective that it melts the ice from the inside out, creating global, liquid water oceans trapped between a rocky seafloor and a ceiling of ice that can be miles thick. It's a remarkable paradox. These moons are so far from the sun that their surfaces are among the coldest places in the solar system, yet beneath the frozen crust, they are warm, wet, and potentially teeming with the ingredients for life. The first stunning confirmation that these hidden oceans were real came from a small, icy moon of Saturn named Enceladus. When the Cassini spacecraft arrived at Saturn, scientists expected Enceladus to be a frozen, geologically dead world. Instead, they witnessed one of the most spectacular sights in the solar system: gigantic geysers of water vapor and ice crystals erupting from massive fractures near its south pole, shooting hundreds of miles into space. Cassini didn't just photograph these plumes, it daringly flew right through them, sampling their composition. The analysis was breathtaking. The plumes were not just pure water. They contained simple organic compounds like methane and propane, along with salts and silica nanoparticles. Most importantly, the spacecraft detected molecular hydrogen, a key chemical signature that suggests ongoing hydrothermal activity on the Moon's rocky seabed. On Earth, hydrothermal vents are bustling oases of life that thrive completely independent of sunlight, powered by chemical energy. Enceladus, it appears, has all the necessary ingredients: liquid water, organic molecules, a source of chemical energy, and the right chemistry. It is, in essence, offering us free samples of its hidden ocean, spraying them out into space for us to collect. Jupiter's moon, Europa, presents an equally compelling, though more secretive, case. While it doesn't have the same obvious, continuous plumes as Enceladus, evidence from telescopes and spacecraft like the Hubble Space Telescope suggests it too occasionally vents its subsurface water into space. Galileo mission data strongly indicates that Europa possesses a massive global ocean, containing perhaps twice as much liquid water as all of Earth's oceans combined, all hidden under an icy shell crisscrossed with cracks and ridges. The upcoming Europa Clipper mission, scheduled to launch in the coming years, is designed to be our dedicated detective for this mysterious world. It will fly by Europa dozens of times, using a powerful suite of instruments to peer through the ice with radar, analyze the composition of the surface and any potential plumes, and precisely measure the Moon's gravitational field to confirm the ocean's depth and salinity. Its primary mission is to determine if Europa's ocean has the conditions suitable for life. This leads to one of the most fascinating questions in all of science. If life does exist in these sunless, high-pressure abysses, what would it look like? Without photosynthesis to form the base of the food chain, any ecosystem would almost certainly be chemosynthetic, drawing energy from chemical reactions, just like the bizarre communities found around hydrothermal vents on Earth's ocean floor. There, in total darkness under crushing pressure, entire ecosystems flourish. Giant tube worms, blind shrimp, and strange microbes thrive on the minerals and heat seeping from the Earth's crust. Life on Europa or Enceladus could be similarly exotic. Perhaps it would consist of vast, drifting fields of microbes or filter-feeding organisms anchored to rocky outcrops on the seafloor. They might utilize chemicals like sulfur or methane in their metabolism instead of oxygen. Their forms could be utterly alien, perhaps without eyes, relying on other senses like sensitivity to pressure changes or electrical fields to navigate their perpetual night. The possibility even exists that life there could be based on a completely different biochemistry, using a solvent other than water, though that remains more speculative. The exploration of these ocean worlds does more than just search for new life. It fundamentally expands our definition of what a habitable world can be. For centuries, we focused on the Goldilocks zone around stars, the narrow orbital band where temperatures are just right for liquid water on the surface. Europa and Enceladus teach us that habitability is not just about distance from a star. It can be generated from within, by the gravitational dynamics of a planetary system. This revelation opens up a vast new array of potential homes for life throughout our galaxy. Icy moons orbiting giant planets could be incredibly common around other stars, each one a potential oasis in the cold dark of space. As we prepare to probe these hidden oceans, our gaze is also pulled back inward, to a much closer and familiar world that may also hold secrets to life's tenacity. While the hidden oceans of Europa and Enceladus represent one of the most promising frontiers in the search for life, there is another world, much closer and far more familiar, that has captivated our imagination for centuries: Mars. The red planet has transformed in our understanding from a mere point of light in the sky to a complex world with a history strikingly similar to early Earth. Orbital imagery has revealed a landscape sculpted by water, dry riverbeds snaking across its surface, vast deltas where ancient rivers once emptied into lakes, and mineral deposits that only form in the presence of persistent liquid water. This evidence paints a picture of a planet that, over 3 billion years ago, was a much warmer and wetter place, with a thicker atmosphere and conditions that were potentially habitable for microbial life. It's this tantalizing possibility that has driven decades of robotic exploration, turning Mars into the most heavily scrutinized planet in our solar system, aside from our own. The current flagship of this endeavor is NASA's Perseverance rover, a sophisticated robotic geologist that landed in Jezero crater in February 2021. Scientists chose this location because orbital data clearly shows it was once a lake, fed by a prominent river delta. A delta on Earth is an excellent trap for sediments and, crucially, for preserving the signs of past life. Perseverance's primary mission is to hunt for biosignatures, not the little green men of science fiction, but subtle chemical, textural, and mineralogical clues that could indicate ancient microbial organisms once thrived there. The rover is equipped with a powerful drill that cores rock samples, seals them in ultra-clean tubes, and deposits them in carefully selected caches on the surface. This collection of Martian material is the first step in an ambitious, multi-mission plan known as the Mars Sample Return Campaign. The goal is for a future mission to retrieve these tubes and launch them back to Earth, where scientists in advanced laboratories around the world can analyze them with instruments far more powerful than anything we can send on a rover. This would allow us to conduct the most definitive search for evidence of past life that we have ever undertaken. Adding a layer of compelling intrigue to the search for past life is the ongoing mystery of present-day methane in the Martian atmosphere. On Earth, the vast majority of methane is produced by biological processes, from microbes in wetlands to the digestive systems of livestock. So, when telescopes and orbiting spacecraft, and later the Curiosity rover on the surface, detected occasional, transient plumes of methane gas, the scientific community was electrified. Could this be a sign that microbial life is not just a relic of the past, but is still alive today, perhaps hidden deep underground in aquifers shielded from the harsh surface radiation, and is periodically releasing this gas? However, the story is not so simple. Methane can also be produced through purely geological processes such as serpentinization, a reaction between water, carbon dioxide, and certain types of rock that occurs in the absence of any biology. Determining the source of this methane is one of the most pressing puzzles in planetary science. Future missions will need to not only detect the gas, but also analyze its isotopic signature. Methane from biological sources tends to have a different ratio of carbon isotopes than methane produced geologically. Solving this puzzle could either point us toward a hidden biosphere or reveal a new, fascinating type of geology. This leads to one of the most profound questions we could possibly answer. If we do find conclusive evidence that life once existed or still exists on Mars, did it arise independently? Or does it share a common origin with life on Earth? This is the heart of the panspermia hypothesis. We know that throughout the history of the solar system, impacts have blasted material from the surface of both Mars and Earth into space. Martian meteorites have been found on Earth, proving that this exchange is possible. It is entirely feasible that a rock carrying resilient microbes could have been ejected from a young Mars by an asteroid impact, journeyed through space, and eventually landed on a young, habitable Earth, seeding our planet with life. If future analysis of Martian life reveals it uses the same biochemical machinery, the same DNA, the same amino acids, it would be powerful, though not conclusive, evidence that we might all be Martians originally. Conversely, if Martian life is based on a different biochemistry using different nucleotides in its genetic code or a different handedness in its amino acids, it would strongly suggest a second, independent genesis of life. This single data point would revolutionize our understanding of life's place in the universe, telling us that the transition from chemistry to biology is not a miraculous fluke, but a common and perhaps inevitable process wherever the right conditions persist. The search on Mars is therefore about much more than just one planet. It is a quest to understand the universality of life itself. Every drill core, every atmospheric measurement, and every image of an ancient shoreline brings us closer to answering whether life is a cosmic imperative or a solitary accident. The lessons we learn from exploring its rust-colored deserts directly inform how we will investigate the more distant, icy ocean worlds, providing a crucial bridge in our understanding of habitability across the solar system and beyond. Beyond the familiar rocky worlds and gas giants lies a class of planet that is both mysterious and misunderstood: the ice giants. Uranus and Neptune, the sentinels of our solar system's outer darkness, are not merely smaller versions of Jupiter and Saturn. They are fundamentally different, a distinct class of world that represents the most common type of planet we now know exists around other stars. Yet, for all their prevalence across the galaxy, they remain the least explored planets in our own celestial backyard. Our only close-up encounter was a fleeting visit more than 3 decades ago, when Voyager 2 performed a grand tour of the outer solar system, giving us just a brief glimpse of each world before continuing its lonely journey into interstellar space. What we learned in those short flybys was enough to completely reshape our understanding of planetary science and leave us with a host of profound new questions. The most striking feature of both planets is their beautiful, deep azure color, a serene appearance that belies the violent conditions within their atmospheres. This iconic blue hue comes from the presence of methane gas. The upper atmospheres of both planets contain this compound, which acts like a cosmic filter. It absorbs the red wavelengths of sunlight and efficiently scatters the blue light back into space, painting the entire planet in varying shades of cerulean and cobalt. But if you could descend below these cloud tops, you would encounter conditions so extreme they challenge our very understanding of matter itself. Deep within these planets, where pressures mount to millions of times that of Earth's surface and temperatures soar to thousands of degrees, water is believed to exist in a bizarre, exotic state known as supersonic water. Imagine a form of water where the immense pressure has shattered the familiar molecular structure, locking the oxygen atoms into a rigid, crystalline lattice, a solid, while the hydrogen ions are freed to flow through this lattice like a liquid. This substance is both a solid and a liquid simultaneously, a highly conductive fluid that is thought to be the source of the ice giants' unusual and complex magnetic fields. The dynamics of these two worlds, while similar in some ways, are also strikingly different, presenting a compelling comparative puzzle. Uranus is the solar system's oddball, a world that seems to have been knocked on its side. Its axis of rotation is tilted a staggering 98 degrees, meaning it essentially rolls around the Sun on its side. This leads to the most extreme seasons imaginable. For a quarter of its 84-year orbit, one pole is plunged into continuous, decades-long darkness, while the other pole bakes under unending sunlight. The mechanisms behind this dramatic tilt remain one of the great unsolved mysteries. The leading theory suggests a cataclysmic collision with an Earth-sized protoplanet in the early, violent days of the solar system, an impact so colossal it literally tipped the world over. Neptune, by contrast, spins on a more conventional axis but possesses an atmosphere that is anything but calm. Despite receiving only 3% of the sunlight that Jupiter gets, Neptune boasts the fiercest winds in the solar system, with gusts screaming near its equator at speeds exceeding 1,200 miles per hour. These are supersonic winds, powered not by the sun's warmth but by the intense heat still radiating from the planet's own interior, left over from its formation. This internal engine also drives massive storm systems, like the famous Great Dark Spot observed by Voyager 2, a hurricane-like storm the size of Earth that mysteriously vanished by the time the Hubble Space Telescope later looked for it. The brief Voyager 2 flybys were like seeing two masterpieces in a dark room with only a flicker of lightning to illuminate them. We saw enough to know they are breathtaking, but not enough to understand their true nature. This lack of data is why planetary scientists are so passionately advocating for a dedicated mission to return to the ice giants. Proposals for orbiters like the NASA concept studies for a Uranus orbiter and probe envision a spacecraft that would enter orbit around Uranus and deploy an atmospheric probe to plunge directly into its clouds, sampling its composition in situ for the first time. The scientific returns would be monumental. These worlds are thought to be pristine time capsules, holding frozen clues about the composition and conditions of the outer protoplanetary disk from which all the planets formed. Understanding their interior structure, atmospheric dynamics, and magnetic fields is not just about satisfying curiosity about our own solar system. It is the key to understanding a vast class of planets we see orbiting other stars, worlds we call mini-Neptunes that appear to be among the most common types of planet in our galaxy. And the intrigue does not stop at the planets themselves. Their moon systems, though not as vast as Jupiter's or Saturn's, hold their own tantalizing secrets. Uranus's moon Miranda looks like a cosmic jigsaw puzzle pulled apart and hastily reassembled, with bizarre fault canyons and coronae that suggest a violent and complex geological history. Neptune's large moon Triton is a captured object from the Kuiper belt, a world that orbits backwards relative to its planet's rotation and is one of the few geologically active worlds in the outer solar system, with cryovulcanos spewing nitrogen ice into its thin atmosphere. Could any of these moons hide subsurface oceans warmed by the gravitational tug of their giant parents? It is a distinct possibility that future missions will be eager to investigate. By unraveling the secrets of Uranus and Neptune, we do more than just complete the map of our own solar system. We unlock the fundamental principles that govern the formation and evolution of planets everywhere, providing the essential context for the thousands of icy worlds we are discovering in the great beyond. To truly grasp the grand architecture of our solar system, we have to rewind the cosmic clock back some 4.6 billion years to a time before the Sun and planets even existed. Our story begins in a sparse, cold cloud of interstellar gas and dust, a nebula likely nudged into collapse by the shockwave from a nearby supernova explosion. As this giant cloud began to contract under its own gravity, it started to spin faster, much like a figure skater pulling in their arms, flattening out into a vast, spinning disk of material called the solar nebula. At the hot, dense center of this whirling disk, pressures and temperatures soared to unimaginable levels, eventually triggering nuclear fusion and igniting our sun. Meanwhile, out in the cooler, thinner regions of the disk, the leftover gas and dust began a slow, patient dance of accumulation. Tiny particles of dust and ice stuck together, forming ever larger clumps called planetesimals. These, in turn, collided and merged, growing through a process of accretion to eventually form the planets, moons, asteroids, and comets we know today. This overarching framework, known as the Nebula Hypothesis, provides the beautiful, elegant backbone for our origin story. But as with any good story, the devil and the true wonder is in the fascinating details. While the nebula hypothesis gives us the broad strokes, it doesn't explain the specific, quirky architecture of our solar system. Why are the small, rocky planets like Earth and Mars clustered close to the Sun, while the giant gas and ice worlds orbit much farther out? The answer appears to be a dramatic period of planetary migration and gravitational upheaval in the solar system's youth. One of the most compelling theories to explain this is known as the Grand Tack model. This idea suggests that in its infancy, Jupiter, the solar system's largest planet, began to form at a distance of about 3.5 times the Earth-Sun distance. As it interacted with the gas and planetesimals in the disk, it started to migrate inward toward the Sun, like a massive ship plowing through cosmic waters. This inward journey likely went on until Jupiter was roughly at the orbit where Mars is today. Then something crucial happened. Saturn began to form behind it. As Saturn grew, its gravity locked into a specific orbital resonance with Jupiter. This gravitational tug of war between the two giants effectively reversed Jupiter's course, causing it to migrate back outward to its current position. This grand tack, this inward and then outward journey, had profound consequences. Jupiter's gravitational wake would have scattered material, potentially explaining why Mars is so much smaller than Earth and Venus, and why the asteroid belt between Mars and Jupiter exists but is so sparsely populated. It was a gravitational dance of epic proportions that literally sculpted the inner solar system. The evidence for these ancient, chaotic events isn't just locked in computer models. We hold pieces of it in our hands. Meteorites, the rocky debris that falls to Earth from space, are invaluable time capsules. Many of these are primitive chunks of asteroids that have remained largely unchanged since the very dawn of the solar system. When scientists analyze them with incredibly precise instruments, they find within them tiny, microscopic grains of stardust pre-solar grains. These are minerals like silicon carbide and nanodiamonds that formed in the atmospheres of dying stars long before our sun was born. They were blasted into space by stellar winds and supernova and were later incorporated into the solar nebula. These resilient grains are literally older than our solar system itself, and their presence tells us that our cosmic neighborhood was built from the recycled remains of earlier generations of stars. Furthermore, by studying the ratios of different isotopes in meteorites, scientists can create a kind of chronological timeline, revealing that the first solid materials in the solar system condensed within a remarkably short window, perhaps less than 200,000 years. This suggests the initial stages of planet formation were incredibly rapid and dynamic. Other anomalies in our solar system point to a violent and turbulent infancy. The Late Heavy Bombardment is a proposed period around 4 billion years ago when the inner planets were seemingly pummeled by a sudden spike in asteroid and comet impacts, leaving behind the cratered landscapes we see on the Moon and Mercury today. What could have caused such a dramatic deluge? The most likely explanation is another gravitational rearrangement of the giant planets. As Jupiter and Saturn migrated into their final orbits, their immense gravity could have destabilized the distant reservoirs of icy bodies in the Kuiper belt and the Oort cloud, flinging a barrage of them inward toward the Sun. And then there's the curious case of Uranus, which spins almost perfectly on its side with an axial tilt of 98 degrees. Such an extreme orientation is almost certainly the result of a colossal collision with an Earth-sized protoplanet in the early solar system, a catastrophic impact that literally knocked the world over. These clues force us to ask an even more speculative question. Was our solar system's family once larger? Some planetary scientists have proposed the existence of a fifth giant planet, similar to Neptune, that was gravitationally ejected from the solar system entirely during this period of instability, sent flying out into the lonely interstellar dark. This is not as far-fetched as it sounds. We have since observed rogue planets drifting freely in space between the stars. Understanding the often chaotic and violent processes that shaped our own solar system is not just an exercise in ancient history. It is the essential key to unlocking the mysteries of the thousands of exoplanetary systems we are now discovering. When we look at other stars, we see an incredible diversity of planetary architectures: hot Jupiters orbiting blisteringly close to their suns, systems with planets packed into tight, resonant orbits, and others with worlds on wildly eccentric paths. Our own solar system, once thought to be the standard model, now appears to be just one possible outcome of planet formation. By deciphering our own history, including the migrations, collisions, and ejections, we learn how to interpret the stories of these distant systems. This knowledge directly informs the search for other Earth-like worlds. We learn what factors create stable, habitable zones, and how common such serene conditions might be in a galaxy where planetary billiards seems to be the norm. This investigation into our own origins naturally draws our attention to the small, leftover building blocks that never formed planets, the asteroids and comets that are the preserved remnants of that primordial disk. These small, wandering remnants are far more than just cosmic debris. They are the preserved building blocks of our solar system, frozen time capsules holding secrets from over 4.6 billion years ago. Unlike the planets which have been transformed by billions of years of geological activity, many asteroids and comets have remained almost pristine, offering us a direct line back to the very beginning. Think of them as the leftover ingredients from a grand recipe, scattered on the counter after the planets had finished baking. By studying them, we can learn not only what went into making our cosmic neighborhood, but also how those ingredients came together in the first place. Our quest to understand these primitive objects has moved from distant observation to intimate contact. Recent robotic missions have achieved what was once the stuff of science fiction. They have traveled to these small worlds, touched their surfaces, and brought pieces of them back to Earth. Japan's Hayabusa 2 mission performed a breathtaking ballet around the asteroid Ryugu, a dark, diamond-shaped world rich in carbon. It didn't just land, it fired a small projectile into the surface to stir up material before swooping in to capture it. NASA OSIRIS-REx mission performed a similar delicate operation on the asteroid Bennu, which surprised scientists by having a surface that behaved more like a plastic ball pit than solid rock. The samples returned from these missions are already revolutionizing our understanding. Inside them, scientists have found a rich array of organic compounds, including amino acids, which are the fundamental building blocks of proteins essential for life. Perhaps even more significantly, they found evidence of water-bearing minerals. This provides the strongest evidence yet for a theory called panspermia, which suggests that the basic ingredients for life may have been delivered to a young, dry Earth by countless asteroid and comet impacts early in our planet's history. We may literally be made of stardust, assembled in part from materials forged in the cold depths of space. While asteroids are generally rocky and metallic, comets are the icy travelers from the solar system's outer darkness. Often called dirty snowballs or icy dirt balls, they originate in the distant Oort cloud or the Kuiper belt. As a comet's elongated orbit brings it closer to the sun, the heat causes its frozen ices, water, carbon dioxide, methane, to transform directly into gas, a process called outgassing. This gas, mixed with dust, erupts from the surface, creating the comet's magnificent, glowing coma and its iconic tails, which can stretch for millions of miles. These tails are like a cosmic fingerprint, and by analyzing their light with spectrometers, astronomers can determine their exact composition. This tells us about the conditions and chemistry of the primordial solar nebula from which the sun and planets condensed. The European Space Agency's Rosetta mission took this a step further, actually orbiting the comet 67P/Churyumov-Gerasimenko and deploying a lander Philae to its surface. Rosetta discovered that the water on this comet had a different ratio of hydrogen isotopes than water on Earth, complicating the simple story of our oceans being delivered solely by comets. It also detected the amino acid glycine and phosphorus, another key element for life, reinforcing the idea that these icy messengers could have seeded young worlds with the prerequisites for biology. The study of these small bodies is not without its profound surprises, some of which challenge our understanding entirely. In 2017, astronomers using the Pan-STARRS telescope in Hawaii detected an object unlike any other. It was moving too fast to be bound by the Sun's gravity, meaning it was not from our solar system. This was the first known interstellar visitor, later named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. Its properties were bizarre. It had an elongated, cigar-like shape, and as it sped away from the Sun, it exhibited a slight but unexpected acceleration that couldn't be explained by gravity alone. The most natural explanation was that it was outgassing like a comet, but no coma or tail was ever observed. Its dry, rocky appearance was more asteroid-like, but its acceleration was cometary. This led to a flurry of scientific papers trying to explain its nature, with some suggesting it could be a hydrogen iceberg or a dust bunny-like aggregate of material. The mystery was so deep that a few scientists, including Harvard's Avi Loeb, cautiously raised the possibility that it could be an artificial object, like a light sail from another civilization. While most astronomers favor a natural origin, Oumuamua's true nature remains an open question, a thrilling reminder that the universe is still full of wonders we have yet to classify. Beyond their scientific value, these objects also command our attention for a much more immediate reason. They are a tangible threat. The same process that delivered the ingredients for life also periodically brings destruction. The craters scarring the Moon, Earth, and every other rocky body are silent testimony to a violent past, and the future holds more impacts. The event that wiped out the dinosaurs 66 million years ago was caused by an asteroid estimated to be 6 miles wide. A similar impact today would be catastrophic for human civilization. This sobering reality has given rise to the field of planetary defense. Agencies like NASA, a Planetary Defense Coordination Office, are actively cataloging and tracking near-Earth objects, building a database of potential hazards. The Double Asteroid Redirection Test, or DART mission, was a landmark experiment in this effort. It successfully crashed a spacecraft into the small moonlet of the asteroid Dimorphos, proving that we could measurably alter the orbit of a celestial body through kinetic impact. This was humanity's first test of a potential technique to nudge a threatening asteroid off a collision course with Earth, transforming us from passive observers into active stewards of our planet's safety. The knowledge we gain from studying the composition and structure of asteroids is vital for designing such deflection strategies, as a loose rubble pile would respond very differently to an impact than a solid metal rock. Our exploration of these ancient relics is therefore not just about understanding our past. It is fundamentally about securing our future. But the threat from above is not limited to asteroids alone. Our own sun, the source of life-giving energy, can also turn against us with sudden, violent outbursts. A massive solar flare, an eruption of intense radiation, or a coronal mass ejection. A billion-ton cloud of magnetized plasma launched from the sun's surface could have devastating consequences for our technology-dependent civilization. The most famous example of this, the Carrington event of 1859, caused telegraph systems across Europe and North America to fail. with operators receiving shocks and telegraph paper catching fire. A storm of that magnitude today would be catastrophic, inducing powerful electrical currents in our vast power grids, potentially frying transformers and causing continent-wide blackouts that could take months or even years to repair. Beyond the grid, such an event could disable satellites, crippling global communications, GPS, and weather monitoring. The economic and societal impact would be immeasurable, setting humanity back decades in an instant. While we now have early warning systems like the Deep Space Climate Observatory satellite, which can provide about 30 minutes of notice, our ability to weather such a storm depends entirely on the resilience of our infrastructure, a vulnerability we are only beginning to address. Looking beyond our solar system, the cosmos harbors even more extreme and unpredictable dangers. A gamma-ray burst is the most powerful known explosion in the universe, a concentrated beam of energy released during the collapse of a massive star or the merger of two neutron stars. If one were to occur within a few thousand light-years of Earth and its jet were pointed directly at us, the effects would be apocalyptic. The high-energy radiation would violently rip apart the ozone layer that protects life from the sun's ultraviolet rays. Without this shield, the surface of the planet would be bathed in deadly radiation, triggering mass extinctions and potentially collapsing the entire food chain. The good news is that such events are incredibly rare in our galactic neighborhood, and the chances of one being aimed at Earth are vanishingly small. Similarly, a nearby supernova, the explosion of a dying star, could have similar ozone-depleting effects if it occurred within about 50 light-years. While there are no stars that close that are currently poised to explode, it's a reminder that we exist in a dynamic and sometimes violent galaxy. So, how prepared are we for these cosmic threats? The answer is a mixed bag of remarkable progress and sobering vulnerability. For the most immediate and predictable danger, asteroid impacts, our planetary defense capabilities are advancing rapidly. The successful DART mission proved that we can, in principle, deflect a threatening object. The next step is to develop and test a wider toolkit of deflection methods, which might include gravity tractors, using a spacecraft's own gravitational pull to gently tug an asteroid off course over time, or focused ion beams. But the key to any defense is early warning. We need a comprehensive and continuous census of all near-Earth objects, a task that requires powerful ground-based telescopes like the upcoming Vera Rubin Observatory and, ideally, a dedicated space-based infrared surveyor that can spot asteroids lurking in the direction of the Sun, a blind spot for Earth-based observers. For threats like solar storms, preparedness is less about deflection and more about hardening our critical infrastructure. Utilities can install grid-blocking devices to prevent cascading failures, and satellite operators can design their systems to enter safe modes during intense solar activity. The challenge is the cost and the political will to implement these protections before a disaster strikes, not after. The most extreme events, like a nearby gamma-ray burst, are simply beyond our current capacity to mitigate. They serve as a humbling reminder of our fragile place in the cosmos. This collective awareness of our planetary vulnerabilities is perhaps the most powerful catalyst of all. It forces a profound shift in perspective, moving us from thinking of Earth as a permanent, impregnable home to recognizing it as a single planet in a universe that can be both beautiful and hostile. This realization doesn't just drive the development of planetary defense. It fundamentally fuels the human imperative to become a multi-planetary species, to ensure that the story of humanity is not tied to the fate of a single world. Establishing a permanent human presence beyond Earth is perhaps the most ambitious and necessary endeavor we have ever contemplated. a monumental leap that transforms us from a single-planet species into a multi-planet civilization. This isn't just about planting flags and leaving footprints. It's about building homes, raising families, and creating sustainable societies in the most hostile environments imaginable. The challenges are not merely technical puzzles to be solved. They are fundamental tests of our biology, our psychology, and our very humanity. Every aspect of life as we know it must be re-engineered from the ground up, starting with the most immediate threats. In the void of space or on the barren surface of Mars, there is no protective atmosphere or magnetic field to shield us from the constant, deadly rain of cosmic radiation and solar flares. This invisible barrage can damage DNA, increase cancer risks, and harm the central nervous system. Shielding a colony will require immense ingenuity, from burying habitats under meters of Martian regolith or lunar soil to developing advanced materials with magnetic fields that can mimic Earth's protective bubble. Beyond the physical barrier of radiation lies the intricate challenge of simply staying alive. A colony must become a perfectly balanced, closed-loop ecosystem, a tiny, fragile bubble of earthly conditions in an infinite desert of nothingness. Every breath of air, every drop of water, and every morsel of food must be meticulously recycled and regenerated. Projects like NASA's Advanced Closed-Loop System on the International Space Station are already testing technologies to scrub carbon dioxide from the air and convert it back into oxygen. Water recovery systems must achieve near-perfect efficiency, purifying and reusing every ounce from humidity, sweat, and urine. And then there is food. Astronauts on the ISS rely on regular resupply missions, but a true colony must be self-sufficient. This means mastering hydroponics and aeroponics to grow crops under artificial suns, potentially using genetically modified plants engineered for higher yields and greater nutrient density in alien soil. The concept of in-situ resource utilization is key to this survival. Instead of hauling every kilogram of building material from Earth at astronomical cost, we will learn to use what is already there. Regolith, the dusty soil covering the Moon and Mars, can be processed and used in massive 3D printers to construct habitats, one layer at a time, providing robust protection against radiation and micrometeorites. Yet, the most profound challenges may not be the engineering of machines, but the engineering of human society itself. Imagine a group of people, selected for their physical and mental resilience, embarking on a one-way journey to a world where they will be utterly dependent on each other and their technology for survival. The psychological strain will be immense. They will experience crushing isolation, severed from the sights, sounds, and emotional connections of Earth, watching their home planet shrink to a mere pale blue dot. Confinement in cramped quarters, the constant threat of catastrophe, and the lack of sensory variety could lead to depression, conflict, and cognitive decline. How do we design habitats that are not just functional, but psychologically nurturing? How do we maintain group cohesion and mental health when a quick return home or a reassuring video call is impossible due to communication delays that stretch to 20 minutes or more? These are not abstract questions. They are the focus of analog missions on Earth, where crews are isolated in habitats in the Arizona desert or submerged undersea for months at a time, simulating the conditions of a distant world to better understand the human factor. This grand venture is already moving from science fiction to concrete planning. NASA's Artemis program aims to return humans to the Moon, not for brief visits, but to establish a sustainable base camp at the lunar South Pole, a region believed to hold water ice in its permanently shadowed craters. This lunar outpost will serve as the ultimate proving ground, a place to test the technologies and operational procedures needed for the much greater challenge of a journey to Mars. The lessons learned on our celestial doorstep will be invaluable for surviving the months-long transit and the harsh reality of the red planet. But this new chapter of exploration is no longer the sole domain of governments. Private companies like SpaceX are driving the vision forward with ambitious plans for Starship, a colossal vehicle designed to carry large numbers of settlers and massive amounts of cargo to Mars, fundamentally changing the economic model of space travel. As we stand on the precipice of becoming an interplanetary species, we are forced to confront deep and complex ethical questions that we have never had to answer before. How will these new societies govern themselves? Will they operate under the laws of their founding nations, or will they develop their own unique systems of governance, tailored to their extreme environment? What rights will the first settlers have, and what responsibilities will they bear? The concept of planetary protection becomes a two-way street. We must ensure we don't contaminate other worlds with earthly microbes that could destroy any nascent alien life, but we must also consider our right to alter an entire planet for our own habitation. This leads to the ultimate terraforming dream. Could we one day engineer Mars to have a thicker atmosphere, liquid water on its surface, and a warmer climate, effectively creating a second Earth? The process would take centuries, if not millennia, and raises profound questions about our role as stewards or conquerors of worlds. Alternatively, visionaries like Gerard O'Neill proposed building massive, free-floating space colonies, enormous cylinders that rotate to simulate gravity, filled with parks, lakes, and cities, housing millions of people in orbit around the Earth or Sun. These endeavors represent far more than a technical challenge. They are the next logical step in the human story of exploration and migration, a journey that ties directly into our deepest quest to understand if we are alone and to ensure that the light of consciousness never flickers out. While the search for microscopic life focuses on chemistry and biology, there exists an entirely different and equally thrilling quest, one that listens for the whispers of intelligence itself. This is the hunt for technosignatures, the detectable signs of advanced technology crafted by civilizations far beyond our own. Instead of scanning for the subtle biomarkers of microbes, scientists here are tuning their instruments to find evidence of engineering on a staggering scale. We're talking about things like powerful, focused radio signals deliberately beamed across the galaxy, or incredibly bright pulses of laser light used for interstellar communication. The imagination really soars when we consider the possibility of detecting megastructures, colossal artifacts built around stars to harness their energy, like the legendary Dyson Sphere, a vast swarm of orbiting panels that would completely enclose a star, causing its visible light to dim and its infrared heat to radiate intensely. Finding any one of these would be the most profound discovery in human history, an undeniable sign that we are not the only thinkers in the cosmos. The history of this search is filled with tantalizing, unresolved mysteries that continue to captivate us. The most famous of these is the WOW signal, detected one summer night in 1977 by the Big Ear radio telescope in Ohio. The signal was a narrowband radio burst, exactly the kind predicted to come from an artificial source, and it was so powerful that the volunteer astronomer who found it, Jerry Amon, circled it on the printout and simply wrote, "Wow." Next to it, it came from the direction of the constellation Sagittarius and lasted for a full 72 seconds, but despite numerous attempts, it was never heard again. While most astronomers believe it was likely a natural, albeit extremely rare, phenomenon, perhaps a comet that wasn't accounted for at the time, its perfect characteristics and unexplained nature have cemented its place in the lore of the search for extraterrestrial intelligence. A more recent puzzle emerged with the star KIC 8462852, often called Boyagian star after the scientist who led its study. Data from the Kepler Space Telescope showed that this star was dimming in bizarre, irregular, and dramatic ways, sometimes losing up to 20% of its brightness. One wild theory suggested this could be caused by a partially constructed alien megastructure, like a Dyson swarm, passing in front of the star. However, after years of intense observation, the scientific consensus has shifted toward more natural, if still unusual, explanations, such as a complex cloud of dusty debris from colliding asteroids or a fractured exomoon. Yet, the very fact that such an extraordinary idea was seriously considered shows how our search for technosignatures is pushing us to think bigger and question every anomaly. The tools and strategies for this grand search are evolving far beyond the traditional listening for radio waves. Modern SETI, the search for extraterrestrial intelligence, is becoming a multi-wavelength endeavor. Radio searches continue with more sensitivity than ever, with projects like Breakthrough Listen using some of the world's most powerful telescopes to scan millions of stars across a wider range of frequencies. But scientists are now also conducting optical SETI, using powerful telescopes to look for nanosecond-long laser pulses that could be used as a beacon or for communication between stars. Another approach is to search for signs of industrial pollution in the atmospheres of exoplanets. Could we detect the chemical fingerprints of CFCs or other artificial gases in the light of a distant world? The upcoming James Webb Space Telescope might just have the capability to find such evidence, and the search isn't limited to distant stars. Some researchers are also looking closer to home, scanning the solar system for possible alien artifacts or probes. This concept, sometimes called Dysonian SETI, involves looking for evidence of technology that might be old, abandoned, or so advanced we can barely comprehend its purpose, perhaps lurking in the asteroid belt or in a stable orbit around the Sun. The discovery of a confirmed technosignature would instantly and irrevocably shatter our cosmic perspective. The philosophical and societal implications are almost too vast to comprehend. On a scientific level, it would prove that the emergence of intelligence and technology is not a unique fluke but a possible, perhaps even common, outcome of cosmic evolution. It would provide an existence proof that a technological civilization can survive its own adolescence and avoid self-destruction, offering a desperately needed dose of hope for our own future. The knowledge itself would be transformative. We might gain access to a cosmic library of scientific and technological knowledge millions of years more advanced than our own, solving problems we haven't even encountered yet. But the impact would run much deeper than just information. It would force a fundamental re-evaluation of humanity's place in the universe, challenging every religion, philosophy, and cultural narrative about our uniqueness. Would it unite humanity in a shared identity as Earthlings, or would it create new divisions and fears? The mere act of detection would not bring instant understanding. The message could be incomprehensible or its intent unknowable. Are they peaceful explorers, indifferent observers, or something else entirely? This pursuit, at its core, is the ultimate test of our curiosity and our courage, asking us if we truly want to know the answer to the ancient question of whether we are alone, and preparing us to consider the nature of the minds that might be out there waiting. Now we arrive at one of the most profound and deeply personal mysteries of all, one that lies at the very heart of our experience of the cosmos, the nature of consciousness itself. We've explored black holes, dark energy, and the potential for alien life, but all of those discoveries are filtered through one undeniable reality: our own awareness. We are the universe become self-aware, a collection of stardust that can contemplate its own origins, And this fact raises a staggering question that straddles the line between science and philosophy. Is consciousness merely a happy accident, a byproduct of complex neural computation inside our skulls? Or could it be something far more fundamental, a basic property of the universe woven into the very fabric of reality, much like space and time? This idea is not new, but it's gaining a fresh look from some corners of physics and philosophy. It's called panpsychism, the view that consciousness is a universal and fundamental feature of all things. In this view, consciousness didn't suddenly emerge from unconscious matter at some point in evolutionary history. Instead, it was always there in some rudimentary form. The proposal is that even the most basic entities, an electron, a quark, an atom, possess an infinitesimal spark of subjective experience. Of course, this isn't to say a rock is thinking deep thoughts or a proton is feeling sad. It suggests that experience itself, in its most basic form, might be a property of matter, and that more complex consciousness, like our own, arises from a specific, highly complex integration of these fundamental units of awareness. It's a radical shift from seeing the brain as a generator of consciousness to seeing it as a receiver or amplifier of a consciousness that is already everywhere. While this idea is far from mainstream science and is incredibly difficult to test, it offers a provocative solution to the so-called hard problem of consciousness, explaining how and why we have qualitative, subjective experiences at all. This mystery is inextricably linked to the fine-tuning we discussed earlier through a concept known as the anthropic principle. This principle simply states that the universe must have the properties we observe, because if it didn't, we wouldn't be here to observe it. The fundamental constants are set to values that allow for stars, planets, and ultimately conscious life. The strong version of this principle suggests that the universe is in some sense compelled to eventually produce consciousness, that observers are a necessary part of the cosmic story. This leads to even more speculative ideas, like the participatory anthropic principle, which proposes that the presence of observers is necessary to bring the universe into being. This echoes a strange aspect of quantum mechanics, where the act of observation seems to play a role in determining the state of a system, collapsing probabilities into definite outcomes. At the quantum level, reality seems to exist in a haze of possibilities until it is measured. This has led some prominent physicists to wonder if consciousness itself is not just a passive observer, but an active participant in shaping reality. If that's true, even in some small way, it opens up breathtaking possibilities for advanced civilizations. We often imagine their technology based on physics as we understand it: warp drives, energy beams, megastructures. But what if a truly advanced species has learned to harness consciousness itself? What if their technology is based not on manipulating matter and energy with tools, but on directly shaping reality with thought? Concepts that sound like pure magic to us: telepathy, telekinesis, or even the intentional manifestation of objects, might be a sophisticated application of laws of physics that we are only just beginning to glimpse, laws where mind and matter are deeply intertwined. Perhaps the reason we haven't detected any radio signals or Dyson spheres is because the most advanced civilizations have moved beyond such crude, physical methods of communication and engineering, and now operate on a level that is completely undetectable to our instruments, a level of pure consciousness. This line of thinking naturally brings us to the concept of a cosmic mind, or a noosphere, a global sphere of thought, a collective consciousness of a planet or even a civilization. The Jesuit priest and paleontologist Pierre Teilhard de Chardin proposed that the evolution of the universe is moving toward an ultimate state of complexity and consciousness, a point he called the omega point, where all consciousness converges. In a similar vein, the Russian geochemist Vladimir Vernadsky suggested the noosphere as the third stage in Earth's development, after the geosphere and the biosphere, a stage where human cognition becomes a major geological force. If such a thing is possible on a planetary scale, could it exist on a galactic or even a universal scale? Is the cosmos itself evolving toward a state of self-awareness, with individual conscious beings acting as neurons in a vast cosmic brain? All of these reflections force us to consider a truly humbling possibility. If we were to make contact with an extraterrestrial intelligence, the gap in understanding might not be just one of technology or science, but one of consciousness itself. They might perceive reality in a way we cannot even conceive, experiencing dimensions of existence that are completely closed off to our current mental apparatus. Communication might not involve language or mathematics, but a direct sharing of experience and awareness. Such an encounter would not just give us new information, it would fundamentally expand what it means to be conscious, to be alive, and to be a part of this universe. It would challenge our materialist worldview to its core, forcing a synthesis of science and spirituality that could redefine the human journey for millennia to come. This contemplation of mind and cosmos inevitably draws our gaze forward to the far, far future and forces us to ask what becomes of consciousness when the stars themselves begin to die. From the silent dance of dark matter to the brilliant flash of a supernova, our journey through the cosmos has revealed a universe of breathtaking dynamism and change. But this grand cosmic story, like all stories, must have an ending. Contemplating the ultimate fate of everything that exists is perhaps the most humbling exercise we can undertake, a projection of physics into the far future that reads like the final chapter of an epic novel. The conclusion of this story is not yet written, and the final outcome hinges entirely on the true nature of that most mysterious of forces, dark energy. Its behavior, which we are only beginning to probe, will dictate whether the universe ends with a whisper, a scream, or something else entirely. The most widely accepted forecast, based on our current observations, is a finale known as the Big Freeze or heat death. In this profoundly lonely scenario, the accelerated expansion driven by dark energy continues unchecked forever. Galaxies beyond our local group will be pushed away at ever-increasing speeds, their light stretched beyond the visible spectrum until they effectively vanish from our observable universe. The sky beyond our galactic neighborhood will grow darker and darker, eventually becoming completely black. Within galaxies, the fuel for star formation will eventually be exhausted. Existing stars will burn out one by one like embers in a dying fire. Black holes will slowly evaporate over trillions upon trillions of years through Hawking radiation. The universe will approach a state of maximum entropy, a condition where energy is evenly distributed everywhere and no more work can be done. It becomes a thin, cold, and incredibly dilute sea of particles and radiation, where the temperature approaches absolute zero. In this eternal, silent equilibrium, no new stars are born, no planets form, and all processes that could support life or even complex chemistry grind to a permanent halt. It is a quiet, cold, and desolate end. But what if dark energy is even more strange and powerful than we currently believe? Another, more violent possibility is the Big Rip. This scenario arises if the strength of dark energy actually increases over time, a form known as phantom dark energy. In this case, the repulsive force doesn't just push galaxies apart. It grows so powerful that it overcomes all the forces that hold structures together. First, the acceleration would tear apart galaxy clusters, then individual galaxies. As the end draws near, the relentless expansion would rip apart stars and planets. In the final moments, even atomic bonds would be overcome, tearing apart molecules, then atoms themselves, and finally ripping apart the very fabric of spacetime. The universe would end in a singular, catastrophic moment of dissolution, a violent unraveling of reality itself. While this scenario is considered less likely given current data, it remains a stark reminder of the potent and unpredictable force we are dealing with. There is a third, more cyclical classical ending, the Big Crunch. This was the expected outcome before the discovery of dark energy, based on the idea that the collective gravity of all the matter in the universe would eventually slow and reverse the expansion. In this model, the universe would begin to collapse inward upon itself. Galaxies would start moving toward each other, the cosmic microwave background would heat up as space contracts, and the sky would grow brighter and hotter. The collapse would accelerate, culminating in all matter and energy being crushed back into a singularity, a mirror image of the Big Bang, a fiery end that potentially sets the stage for a new universe to be born from the ashes in a new Big Bang. This idea of a cyclic universe, of an eternal series of expansions and contractions, is compelling and offers a kind of cosmic rebirth. However, the observed acceleration of the expansion makes this particular ending seem unlikely for our universe, unless the nature of dark energy changes dramatically in the distant future. These grand scenarios, unfolding over timescales so vast they defy human comprehension, naturally lead to a deeply human question. What does this mean for the future of life and intelligence? Could any civilization, no matter how advanced, hope to survive the end of the universe? Theoretically, a sufficiently advanced civilization might devise strategies for what is known as cosmic hysteresis. In the face of a big freeze, they might learn to harness the last remaining energy sources, like tapping into the radiation of evaporating black holes to power their existence in a slowly fading reality. Some have even speculated about the possibility of creating a cosmic arc, a contained universe or a bubble of stabilized spacetime to escape into, or finding a way to jump into another universe within a hypothesized multiverse. These ideas are, of course, the stuff of the most extreme theoretical physics and science fiction, but they speak to a fundamental drive to persevere, to ensure that the light of consciousness, having taken so long to ignite, does not simply flicker out. Ultimately, these visions of the far future are more than just scientific predictions. They are a mirror. They force us to reflect on our own legacy, not in terms of monuments or empires, but in terms of knowledge and understanding. Our efforts to comprehend dark energy and the fate of the cosmos, undertaken over the briefest sliver of cosmic time, are an attempt to read the final page of a story we are only just beginning to understand. This grand cosmic perspective, stretching from the first moment of creation to the very last, inevitably draws our attention to the stage upon which this entire drama unfolds, a dimension so familiar and yet so deeply mysterious that we often take it for granted. Yet for all its power in shaping our reality, time remains one of the most slippery and paradoxical concepts in all of physics. Our everyday experience is one of an inexorable flow, a river carrying us from a fixed past into an uncertain future. We feel time passing, we remember what was, and we anticipate what will be. This seems so fundamental, so obvious, but when we turn to the equations of physics, this flow vanishes entirely. In Einstein's theory of relativity, time is woven together with the three dimensions of space into a single, four-dimensional fabric called spacetime. In this block universe view, all of time, past, present, and future exists simultaneously. The flow is an illusion. The entire history of the cosmos is just a static, unchanging structure. This isn't just philosophical musing. It's a framework that makes incredibly accurate predictions. GPS satellites, for instance, must account for the fact that time literally runs slower in their orbits due to both their speed and the weaker gravity high above Earth, a direct confirmation of relativity's warping of time. So which is real, the flowing time we feel in our bones, or the static time described by our most successful physical theory? This conflict lies at the heart of the mystery. What, then, creates the undeniable directionality we experience, the arrow of time that points from yesterday to tomorrow? The most compelling answer comes not from the realm of relativity or quantum mechanics, but from thermodynamics, specifically the second law. It states that in any closed system, entropy, a measure of disorder or randomness, always increases. Think of an ice cube melting in a glass of warm water. The organized, structured state of the ice cube dissipates into the disordered, randomized state of slightly cooler water. This process is irreversible. You'll never see the warmer water spontaneously form an ice cube while the surrounding water gets hotter. The entire universe is following this same trend, evolving from a state of incredibly low entropy just after the Big Bang, a remarkably smooth and ordered configuration toward a future of maximum entropy and disorder, the heat death we discussed earlier. This increase in entropy is what gives us the psychological arrow of time. We remember the past because it was more ordered, and we cannot remember the future because it is more disordered. It's what gives us a causal arrow where causes always precede effects. But here's the twist: the fundamental laws of physics at the microscopic level are almost entirely time-symmetric. If you were to film two electrons colliding and then play the film backwards, it would look just as valid according to the laws of electromagnetism. The arrow of time isn't written into the fundamental code of the universe. It emerges from the specific, low-entropy initial conditions of the Big Bang. Why the universe began in such a special, ordered state is one of the deepest unanswered questions in cosmology. This strange disconnect between our experience and the laws of physics has led some theorists to propose that time might not be fundamental at all. In the quest for a theory of quantum gravity, a framework to unite the large-scale world of general relativity with the tiny quantum realm, some approaches suggest that time is an emergent property. Loop quantum gravity, for instance, describes space and time as being woven from a network of discrete, finite loops. In this view, the smooth continuity of time is an approximation, much like a digital photograph appears smooth from a distance but is actually made of individual pixels when you zoom in. String theory, another candidate for a theory of everything, often requires the existence of many more spatial dimensions. In some formulations, what we perceive as time could be just one dimension among many, or it could itself emerge from the interactions of more basic, timeless entities. If true, this would be a Copernican-level revolution in our understanding. We once thought Earth was the center of the universe, then we learned it's just another planet. We thought time was a universal background against which events unfold. We may learn that it's a useful illusion that arises from a deeper, timeless reality. This isn't just abstract math. Experiments are being devised to test these ideas, such as looking for subtle blurring in the light from distant gamma-ray bursts that could reveal a pixelated spacetime. This naturally leads to one of the most tantalizing questions in all of science fiction and physics. If time is a dimension, can we travel through it like we travel through space? According to general relativity, the answer is a fascinating and qualified yes for the future, at least. Time dilation is a one-way ticket to the future. If you were to travel at a significant fraction of the speed of light, or orbit closely around a neutron star for a while, time for you would pass much more slowly than for everyone on Earth. You could return after what felt like a few years to find that centuries had passed on Earth. You have effectively jumped into the future. Traveling to the past, however, is infinitely more problematic. Einstein's equations do allow for theoretical structures like wormholes, bridges connecting two distant points in spacetime, or paths known as closed time-like curves that could, in principle, loop back on themselves to create a path to the past. But making this work would require exotic matter with negative energy density to hold the wormhole open, something we have no idea how to create or even if it's possible. And then there are the infamous paradoxes like the grandfather paradox. If you go back in time and prevent your grandfather from meeting your grandmother, you would never be born, so how could you have gone back in time to prevent it? Physics has proposed various solutions, from the idea that the timeline would self-correct to prevent the paradox, to the many worlds interpretation where your actions would simply create a new, parallel branch of reality. For now, time travel to the past remains firmly in the realm of mathematical possibility, a ghost in the equations that may yet be banished by a deeper theory of quantum gravity. Perhaps the most mind-bending possibility of all is that our universe possesses more than one dimension of time. Most of physics is built on the assumption of a single time dimension, but some speculative theories in mathematics and physics entertain the idea of multiple temporal dimensions. What would that even mean? It's incredibly difficult for our brains to conceptualize, locked as we are in a single-track flow of time. In a universe with two time dimensions, the concept of causality could become profoundly complex. An event wouldn't just have a single past and a single future. Its history could form a two-dimensional surface, and its future could be an expanding cone of possibilities. The laws of conservation that govern physics, like the conservation of energy, might break down or take on a completely new form. While there is no experimental evidence for extra time dimensions, and many physicists consider the idea problematic for creating a stable universe capable of supporting life, its exploration pushes the very limits of what we consider possible. It forces us to question the most basic assumptions about reality and reminds us that our perception of time may be a pale shadow of a much richer and more complex structure. This profound mystery, stretching from the psychology of our own consciousness to the edges of theoretical physics, is the final key we need to turn before attempting the ultimate question: what, if anything, came before the beginning of time itself? But if the nature of time itself is so elusive, how can we even begin to ask what came before it? The question of what existed before the Big Bang is perhaps the ultimate challenge to our understanding of reality, pushing us to the very edge of where science can go and where philosophy must begin. For a long time, the query itself was considered nonsensical by many physicists. If the Big Bang was the beginning of spacetime itself, then the concept of a before is like asking what is north of the North Pole, a grammatical construct that simply has no meaning in a physical sense. Time, as we understand it, began at that moment. Yet, the human mind is wired to seek cause and effect, and the sheer improbability of a universe popping into existence from absolute nothingness feels deeply unsatisfying. This has led cosmologists to develop some of the most imaginative and mind-bending theories in all of science, frameworks that attempt to peer beyond the veil of the initial singularity. One of the most profound ideas comes from the work of physicists James Hartle and Stephen Hawking. Their no-boundary proposal is an elegant attempt to eliminate the problem of a beginning entirely. In this model, the universe has no initial boundary in time, much like the Earth has no edge at the North Pole. To understand this, we have to think about the behavior of time near the origin. Hawking and Hartle proposed using a mathematical trick called a Wick rotation, which effectively treats the dimension of time as if it were a dimension of space when we approach the Big Bang. In this view, the universe's past is rounded off like the south pole of a globe. There is no point of creation, no sharp boundary where the laws of physics break down. Instead, the universe just is, a self-contained entity without a singular beginning. In this timeless, four-dimensional geometry, asking what happened before the Big Bang becomes as meaningless as asking what is south of the South Pole. The universe didn't emerge from nothing. It emerged from a smooth, continuous geometry where the distinction between time and space blurs into irrelevance. A completely different, yet equally compelling, set of ideas suggests that our Big Bang was not a unique event, but merely one in an endless series. The cyclic universe model, explored in various forms by thinkers like Roger Penrose, proposes that the cosmos undergoes an eternal cycle of expansion, collapse, and rebirth. In one version, the universe expands outward due to the Big Bang, eventually being pulled back together by gravity in a big crunch. This collapse doesn't end in a singularity of infinite density, but rather rebounds, triggering a new Big Bang and starting the process all over again. Penrose's own conformal cyclic cosmology offers a more exotic variation, suggesting that as our universe expands infinitely into a featureless, empty state, it becomes mathematically identical to the high-energy, dense state of a new Big Bang. In this model, the end of one eon seamlessly becomes the beginning of the next, in an infinite cycle where the arrow of time resets with each new universe. The evidence for this, Penrose claims, might be found in faint, circular patterns in the cosmic microwave background imprints, or Hawking points, left by supermassive black holes from a previous eon. Perhaps the most popular framework for a pre-bang cosmology is the concept of eternal inflation within a multiverse. This theory grows out of the inflationary model we discussed earlier. The idea is that the inflationary field, the energy that caused our universe to expand so rapidly, is eternal. In the vast, frothing quantum foam of a primordial meta-universe, pockets of space can randomly drop to a lower energy state. When this happens, the energy released triggers a hot Big Bang, creating a bubble universe, a self-contained cosmos with its own laws of physics. Our entire universe is just one such bubble in an endless, ever-expanding multiverse, a cosmic foam where new bubbles are constantly being born. In this eternal landscape, there was no first universe and there will be no last. There is always a before because the multiverse itself has always existed, and our Big Bang was simply a local event within this infinite, timeless structure. String theory lends mathematical support to this idea with its vast landscape of possible vacuum states, each one representing a different universe with different physical constants. The most radical proposition of all is that the universe could have arisen from a random quantum fluctuation in a state of true nothingness. This isn't empty space, which is still a something teeming with quantum fields, but a literal nothing, no space, no time, no laws. In quantum mechanics, particles spontaneously pop in and out of existence all the time, borrowing energy from the vacuum for fleeting moments. Could the entire universe be the ultimate example of this quantum uncertainty? If the positive energy of all the matter and radiation in the universe is perfectly balanced by the negative gravitational energy of its own mass, then the total energy of the cosmos could indeed be zero. In that case, it wouldn't require any net energy to come into existence. It could simply be a persistent, large-scale quantum fluctuation that stabilized and grew. From this perspective, the universe is the purest free lunch. Everything we see, from the largest galaxy to the smallest atom, could have emerged from a random ripple in a void of nothingness. The greatest challenge with all of these theories is the search for evidence. How can we test what happened before time began? Some scientists look for clues in the oldest light we can see, the cosmic microwave background. Anomalies like the infamous cold spot, a large, unusually cool region in the sky, could potentially be explained as a bruise from a collision with another universe in the multiverse foam. Others hope that the fledgling field of gravitational wave astronomy might provide a window. Primordial gravitational waves, generated in the first instance of inflation, could carry imprints of the pre-bang geometry, though detecting such ancient signals is a monumental technical challenge. Ultimately, the question of what came before the Big Bang forces us to confront the limits of our language and our logic. We are bound by the concepts of cause and effect, of before and after, which are products of the universe we inhabit. To truly understand its origin, we may need to develop a new physics that operates without the crutch of time, a theory that can finally tell us why there is something rather than nothing. Imagine for a moment that our entire cosmos, with its hundreds of billions of galaxies and its 13.8 billion-year history, is not the whole show. Imagine it is just one single bubble in a vast, frothing cosmic ocean of universes, each with its own unique set of physical laws, its own history, and perhaps even its own bizarre forms of life. This is the breathtaking and controversial idea known as the Multiverse Hypothesis. It suggests that what we have always called the universe is merely a small part of a much larger, more complex, and almost unimaginable reality called the multiverse. This isn't just a wild idea from science fiction. It emerges naturally from several of our most successful, yet incomplete, scientific theories. The theory of cosmic inflation, which so elegantly explains the uniformity and structure of our universe, also predicts that the process of rapid expansion could be eternal. In this eternal inflation, pockets of space could stop inflating at random times, each one undergoing its own hot Big Bang and becoming a separate, self-contained universe, forever isolated from all the others in the ever-expanding inflationary background. String theory, a leading candidate for a theory of everything, adds another layer of support for this mind-bending concept. To be mathematically consistent, string theory requires the existence of many more spatial dimensions than the three we experience. It also predicts a staggering number of possible stable configurations for those extra dimensions, perhaps 10 to the power of 500 different possibilities. Each configuration would result in a universe with different fundamental constants and laws of physics. In this string theory landscape, our universe is just one point in a vast cosmic archipelago, one where the laws of nature happen to allow for stars, planets, and life. This provides a powerful potential explanation for the most perplexing mystery we discussed earlier, the fine-tuning of the universe. If there are an infinite number of universes, each with randomly dialed physical constants, then it's no surprise that we find ourselves in one of the rare habitable ones. We could not exist in any of the others. This application of the anthropic principle doesn't require a fine-tuner. It just requires a multiverse and the sheer statistical power of immensely large numbers. However, this grand vision faces a major and serious criticism from some parts of the scientific community. The central charge is that the multiverse hypothesis is not truly scientific because it seems to be untestable and unfalsifiable. If these other universes are forever beyond our observational reach, causally disconnected from our own space-time, then how can we ever gather evidence to prove or disprove their existence? Critics argue that it risks becoming a philosophical idea disguised as science, a concept that can explain anything but predicts nothing specific about our own world. Proponents of the multiverse counter this by proposing ingenious, though incredibly challenging, ways to look for evidence. One possibility is that if our universe collided with another bubble universe in the distant past, the immense energy released in that impact could have left a permanent, anisotropic scar on the cosmic microwave background. a specific pattern of hot or cold spots that we might one day detect with precise enough instruments. Others suggest that the gravitational waves generated in the first moments of inflation, if ever detected, could carry information about the multiverse that spawned them. The search for such evidence is on the very cutting edge of cosmology. The philosophical implications of confirming a multiverse would be nothing short of earth-shattering. It would be the ultimate Copernican revolution, humbling our place in reality far more than discovering that Earth orbits the Sun or that the Sun is a mere speck in the galaxy. We would have to accept that our entire reality, everything we know and love, is just a tiny fraction of a much grander existence. The laws of physics we have worked for centuries to uncover would be demoted from fundamental truths to mere local bylaws, relevant only in our particular cosmic neighborhood. This realization could open doors to unimaginable diversity, suggesting that every possible universe that can exist does exist. Somewhere out there in the metacosmos, there could be a universe where gravity is repulsive, where time runs backwards, or where the laws of chemistry permit entirely new forms of matter and life beyond our wildest dreams. This concept naturally leads our minds to wander to an even more speculative, but equally fascinating possibility. If a reality can be generated by the random processes of a multiverse, could it also be generated artificially? Could our particular universe, with its seemingly perfect set of rules, be a sophisticated simulation created by an intelligence of almost God-like power? This idea that our reality might not be base reality, but rather an advanced digital construct, is known as the simulation hypothesis. It was thrust into mainstream philosophical debate by Nick Bostrom of the University of Oxford in 2003, and it presents an argument that is as simple as it is unsettling. Bostrom's reasoning begins with a few basic assumptions. First, he assumes that it is at least possible for a civilization to achieve a level of technological maturity so advanced that it could create incredibly detailed, conscious simulations of its own ancestors. Second, he assumes that such a civilization, perhaps out of scientific curiosity, historical research, or even entertainment, would have a desire to run a very large number of these simulations. If both of these premises hold true, then the statistical odds become staggering. The number of simulated minds living in these artificial realities would vastly outnumber the number of biological minds in the original civilization. Therefore, if you are a conscious being, the probability that you are living in a simulation is far greater than the probability that you are living in the base physical reality. This isn't just a thought experiment for philosophers. Some physicists and technologists have begun to seriously consider what potential evidence for such a simulation might look like. The most straightforward place to look would be for what you might call glitches in the matrix, anomalies or shortcuts that a programmer might have used to make the simulation more efficient. For instance, in any complex simulation, there are likely to be resolution limits, perhaps at very small scales like the Planck length, or at very high energy levels. The smooth continuity of spacetime breaks down into a pixelated or discrete nature, revealing the underlying computational grid. Some have even suggested that certain finely tuned constants in physics, which seem so perfectly set to allow for our existence, could be interpreted as parameters chosen by the programmers. Even the strange, observer-dependent outcomes in quantum mechanics, where particles seem to exist in a haze of probability until they are measured, have been pointed to as a potential sign of processing optimization. Details are only rendered when they are needed to be observed, saving immense computational resources. Naturally, this hypothesis is met with intense debate and a fair amount of skepticism. Critics argue that the assumption that any civilization could ever muster the truly astronomical amount of computing power required to simulate an entire universe, complete with every conscious mind within it, is a monumental leap of faith. They also point out that the hypothesis is arguably unfalsifiable in a classic scientific sense. Any potential glitch we find could always be explained away as a feature of base reality we don't yet understand, and the programmers could always patch the simulation to remove any errors we discover. Furthermore, the hypothesis leads to some deeply troubling philosophical questions about the nature of our existence. If this is a simulation, do we have free will, or are our choices predetermined by the code? Is our consciousness real, or is it just an incredibly sophisticated illusion generated by algorithms? What is the purpose of the simulation? Are we part of a grand scientific experiment, a form of historical preservation, or merely entertainment for beings we can scarcely imagine? How we choose to answer those questions could fundamentally alter how we live our lives. If we believe this is all a simulation, does that make our experiences less meaningful or more so? On one hand, it could lead to a sense of nihilism. If nothing is fundamentally real, then why does anything matter? On the other hand, it could be liberating. If this is a constructed reality, then the struggles, the joys, the love, and the art we create are the entire point of the simulation. They are the data, the output, the story. This perspective could inspire us to live more creatively, more compassionately, and with greater curiosity, treating life as the ultimate immersive experience with a purpose we are meant to discover. It reframes the entire human journey not as a random accident in an indifferent universe, but as a narrative within a larger design, making our innate drive to explore and understand the cosmos feel less like a choice and more like a core part of our programmed purpose. This relentless curiosity, this need to push at the boundaries of what we know, might be the most compelling evidence of all that we are part of something far grander than we can currently perceive. This relentless drive to ask why and how is arguably the most powerful engine of human progress we possess. It's the spark that ignited when the first human looked up at a sky filled with points of light and wondered what they were, rather than simply accepting them as a static backdrop. That same spark compelled ancient astronomers across countless cultures to meticulously chart the movements of planets and stars, creating the first predictive models of the cosmos with nothing more than the naked eye and patient observation. This innate curiosity is the common thread connecting the builders of Stonehenge, who aligned their stones with celestial events, to the scholars of the Islamic Golden Age who refined the astrolabe and preserved astronomical knowledge, to the Renaissance thinkers like Copernicus and Galileo who dared to place the sun at the center of our system, fundamentally reordering our place in the universe. Each of these leaps was fueled by a deep, insatiable need to understand the mechanics of the heavens, to push beyond the boundaries of accepted knowledge and see what lay on the other side. This quest for understanding has never been confined to the realm of pure science alone. It is a force that permeates every facet of human expression and endeavor. The same wonder that drives an astrophysicist to calculate the life cycle of a star also inspires a poet to write about the loneliness of space, a painter to try and capture the ethereal glow of a nebula on canvas, and a philosopher to ponder the ethical implications of contacting another civilization. Our curiosity about the cosmos is deeply intertwined with our search for meaning, for purpose, and for our own identity. The questions we ask about the universe are, in their essence, questions we are asking about ourselves. Where did we come from? Are we alone? What is our ultimate fate? This blending of empirical inquiry with profound philosophical and artistic exploration is what makes our journey so uniquely human. It transforms cold data into a narrative, and a collection of facts into a grand story in which we are both the authors and the characters. The tangible fruits of this curiosity are the incredible technologies we have developed to extend our senses far beyond their natural limits. The telescope, first turned skyward by Galileo, was a direct result of this drive to see more, to see further, and to see more clearly. That simple instrument has evolved into a staggering array of eyes on the cosmos, from the Hubble Space Telescope, which has peered back to the earliest galaxies, to the James Webb Space Telescope, which is now analyzing the atmospheres of distant exoplanets. Our curiosity didn't stop with light. We learned to listen to the universe as well, building radio telescopes to detect whispers from the void and gravitational wave observatories to feel the very vibrations of spacetime itself. We built robotic emissaries Voyager, Perseverance, New Horizons, and sent them on journeys across the solar system and beyond, carrying our innate need to explore directly to other worlds. Each of these technologies is a monument to human curiosity, a physical manifestation of our refusal to be bound by our earthly limitations. What is it about the architecture of the human mind that makes us so uniquely predisposed to this kind of exploration? Cognitive scientists suggest it's a powerful combination of pattern recognition, causal reasoning, and a theory of mind that allows us to imagine realities beyond our immediate experience. Our brains are essentially prediction engines, constantly building models of the world and then testing them against reality. When we encounter something that doesn't fit our model, an anomaly in the data, a star that moves differently than the others, it creates a cognitive itch that we are compelled to scratch. This drive to resolve uncertainty, to close the gap between what we know and what we could know, is a fundamental motivator. It's likely that this trait was a key evolutionary advantage, helping our ancestors understand their environment, predict seasons, and navigate vast distances. That same adaptive curiosity has now been turned upon the cosmos itself. This line of thinking leads to a fascinating and hopeful possibility for the search for extraterrestrial intelligence. If curiosity is a powerful adaptive trait that emerges from complex intelligence, then it may be a universal characteristic of any technologically advanced species. A civilization that does not ask questions, that does not look up at its own night sky with a sense of wonder and a desire to understand, might never develop the tools for communication or travel. They would remain isolated on their home world. Therefore, the very act of searching for signals, of sending out probes, and of building telescopes might be evidence of a shared galactic imperative, a common thread of curiosity that binds all intelligent life across the stars. We are, in a sense, broadcasting our curiosity to the universe and listening for an echo of that same quality in return. This reflection on our own driving force naturally compels us to look at how we organize this grand endeavor. The challenges of exploring the cosmos are so vast, so complex, and so expensive that no single nation can hope to tackle them alone for long. The monumental achievements we've celebrated are increasingly the product of shared knowledge, resources, and vision from across the globe. This collaborative spirit, born from our collective curiosity, is perhaps our greatest strength and the key to our future among the stars, a topic that brings us directly to the vital importance of international partnership in space. Perhaps one of the most powerful testaments to our shared curiosity is how it has compelled us to work together on a scale never before seen in human history. What began as a fierce, nationalistic competition during the Cold War has, over the decades, blossomed into a remarkable era of international collaboration in space. The most iconic symbol of this global partnership is undoubtedly the International Space Station, a stunningly complex engineering marvel orbiting 250 miles above our heads. This isn't a project owned by any single nation. It's a shared outpost for humanity, built and operated by a consortium of 5 space agencies: NASA from the United States, Roscosmos from Russia, the European Space Agency representing 22 nations, the Japan Aerospace Exploration Agency, and the Canadian Space Agency. For over 2 decades, this orbiting laboratory has been continuously inhabited by international crews, a living experiment in peaceful coexistence and shared purpose. Astronauts and cosmonauts from across the globe live and work together in an environment where national borders are invisible, and their collective survival depends on mutual trust and cooperation. The station itself is a physical patchwork of modules and components launched by different countries, all interlocking perfectly to form a single, functional home in the void. This partnership does far more than just advance science. It serves as a powerful diplomatic tool, creating unbreakable lines of communication and shared interest between nations that may have political disagreements back on Earth. By pooling financial resources, technical expertise, and intellectual capital, these agencies have achieved something that would have been prohibitively expensive and technologically daunting for any single country to accomplish alone. They share the tremendous risks inherent in spaceflight, ensuring that the burden of a potential tragedy is borne by a community, not a single nation. This model of collaboration has proven so successful that it is now the blueprint for humanity's next giant leaps. The Artemis program, which aims to return humans to the Moon and establish a sustainable presence there, is being built as a global endeavor from the start. NASA has established the Artemis Accords, a set of principles for peaceful and cooperative lunar exploration that has been signed by dozens of countries. The program envisions contributions from around the world. The European Service Module will power the Orion spacecraft. A Canadian robotic arm will be used on the planned Lunar Gateway outpost, and Japanese and European astronauts are slated to walk on the lunar surface alongside Americans. This international framework is not just about sharing costs. It's about weaving a tapestry of shared ownership and common destiny for the future of human space exploration, ensuring that the Moon and beyond are explored for the benefit of all humankind. However, fostering and maintaining this spirit of global cooperation is not without its significant challenges. The world of international space policy is a complex web of different national laws, export controls, and security concerns. Aligning the strategic priorities and budgetary cycles of multiple sovereign nations can be a slow and often frustrating process, requiring immense diplomatic skill and patience. Historical geopolitical tensions on Earth can and do spill over into space partnerships, creating moments of strain and uncertainty. Furthermore, as the era of space commercialization accelerates with private companies like SpaceX, Blue Origin, and a multitude of international startups taking on larger roles, a new dynamic is emerging. We are entering a landscape of both collaboration and competition. While these companies are often crucial contractors for government space agencies, they are also competitors vying for contracts, lunar landing rights, and resource claims. This raises critical questions about how to preserve the ideal of open collaboration between nations while navigating the proprietary and competitive nature of private enterprise. How do we ensure that the pursuit of profit does not create a new form of cosmic colonialism, where access to space and its resources is limited to a few powerful entities? The solution likely lies in developing robust international treaties and frameworks that are updated for the 21st century, establishing clear rules of the road that encourage innovation and investment while safeguarding the principle that space is the common province of humanity. These agreements must strive for equitable benefits, ensuring that the scientific knowledge and economic potential unlocked by space exploration are shared broadly, helping to lift up all of Earth's people and not just a select few. The incredible success of the International Space Station provides a hopeful model for how this can work. It demonstrates that even amid terrestrial disagreements, nations can find common cause in the peaceful exploration of the cosmos. This hard-won spirit of unity, forged in the microgravity of orbit, shows us a path forward for addressing other pressing global challenges, from climate change to pandemic response, proving that our greatest achievements are always the product of working together. This collective responsibility extends beyond how we work with each other and forces us to carefully consider how we interact with any new environments or potential life we might encounter, guiding us toward a new era of planetary stewardship. But as we extend our reach across the solar system, a profound new responsibility emerges, one that moves beyond engineering and into the realm of ethics and planetary stewardship. The moment we step off our pale blue dot, we must confront a critical question: how do we explore without destroying the very things we seek to understand? This is the core of planetary protection, a field dedicated to preserving the integrity of other worlds, especially their potential to teach us about the origins of life itself. The greatest fear is forward contamination, the accidental transport of Earth's hardy microbes to another planet. Imagine a rover like Perseverance, drilling into a pristine Martian rock that may hold fossilized evidence of ancient life, only to have that sample contaminated by a stowaway bacterium from Florida. That single microbe could not only ruin the experiment, but, in a worst-case scenario, could potentially thrive in a new environment, overwhelming any native organisms and irrevocably altering an alien ecosystem before we even have a chance to discover it. To prevent this, space agencies follow strict international guidelines set by the Committee on Space Research, or COSPAR. These protocols require meticulous sterilization of spacecraft, often using intense heat, chemical baths, and assembly in pristine clean rooms to reduce the microbial load to incredibly low levels. For a mission going to a place like Mars or Europa, which have high potential for past or present life, the requirements are exceptionally stringent. This already complex field is becoming infinitely more challenging with the rapid rise of private space missions. Companies planning to land on the Moon or Mars are driven by different timelines and economic pressures than government agencies. While they are subject to national regulations, there is a concern that the profit motive could lead to shortcuts or a less rigorous adherence to planetary protection principles. The Outer Space Treaty of 1967 states that countries must avoid harmful contamination of celestial bodies, but the mechanisms for enforcing this upon private entities are still evolving. This creates a pressing need for new, globally recognized frameworks that ensure commercial exploration is conducted responsibly, balancing the exciting potential of innovation with the solemn duty to protect our shared cosmic heritage. The ethical considerations become even more profound if we actually find life. The discovery of a second genesis of life would be the most monumental event in scientific history, but it would immediately present us with a monumental ethical dilemma. Do we have the right to study it if that study might harm it? If we find microbial life on Mars, should we treat it as a scientific specimen or as a neighbor with its own intrinsic right to exist? The concept of planetary protection would then expand into a form of interstellar environmental ethics. Would it be acceptable to alter its environment for our benefit, a process that could be a precursor to terraforming? And what if we find life that is not just microbial but complex? The potential for discovery on an ocean world like Europa forces us to consider these questions seriously. Our actions in the coming decades could set a precedent for how humanity interacts with extraterrestrial life for all time, making it imperative that we approach this new frontier not as conquerors, but as careful and respectful guests. This mindfulness must extend beyond biology to the very rocks and ice of these other worlds, guiding how we utilize the resources they hold. The vast, silent deserts of the Moon and the countless asteroids drifting through the solar system are far more than just barren rocks. They are untapped treasure chests holding the key to unlocking humanity's future beyond Earth. The dream of space colonization hinges on a simple, practical reality. We cannot afford to haul every drop of water, every breath of air, and every kilogram of building material from the bottom of Earth's deep gravity well. It is astronomically expensive and utterly unsustainable. The solution, instead, is to learn to live off the land, to become cosmic prospectors and miners, extracting the resources we need from the worlds we wish to inhabit. This concept, known as in-situ resource utilization, transforms the entire economic model of space exploration from a series of short, expensive camping trips into a permanent migration. The most precious resource out there isn't gold or platinum. It's something far more mundane and infinitely more vital: water. We've discovered that the Moon, particularly in the permanently shadowed craters at its poles, holds vast deposits of water ice. Asteroids, especially a class known as carbonaceous chondrites, are also rich in water and other volatile compounds. Why is this so revolutionary? Water is the oil of space exploration. It can be split into its constituent elements, hydrogen and oxygen, to create the most powerful chemical rocket fuel known. This means a lunar outpost or a depot on a captured asteroid could effectively become a cosmic gas station, refueling spacecraft and enabling them to travel much farther without the crippling cost of launching all their propellant from Earth. Furthermore, that same water is, of course, essential for human survival, for drinking, growing food, and providing oxygen to breathe. A source of water in space is quite literally a source of life and mobility. Beyond water, these celestial bodies are rich in metallic ores and rare earth elements that are becoming increasingly scarce and environmentally destructive to mine on Earth. An asteroid just a few hundred meters across could contain more platinum group metals than have been mined in all of human history. These materials are crucial not only for building electronics and batteries on Earth, but for constructing habitats, spacecraft, and machinery in space itself. Imagine using massive 3D printers fed with metallic powder processed from lunar soil to autonomously construct a radiation-shielded habitat before the first crew even arrives. This isn't science fiction. Agencies like NASA are actively developing and testing these technologies. The goal is to create a self-sustaining, circular economy in space, where waste is minimized and everything is recycled or sourced locally. This potential has sparked the birth of an entirely new industry, space mining. Companies like the now-defunct Planetary Resources and Deep Space Industries pioneered the vision, attracting investment with the promise of near-limitless resources. While the technical and financial hurdles remain immense, the spark has been lit. We are witnessing the very first steps toward what could become the greatest economic revolution since the Industrial Age. But this budding gold rush hurtles us toward a complex web of legal and ethical questions that we are woefully unprepared to answer. The foundational document for space law, the 1967 Outer Space Treaty, was written at the height of the Cold War with the primary goal of preventing the militarization of space and the nuclear colonization of other worlds. It states that no nation can claim sovereignty over a celestial body, but it says nothing clear about whether a company or a country can own the resources they extract. If an American company mines an asteroid, do those minerals belong to them? What if that asteroid is also being targeted by a Chinese state-owned enterprise? The treaty explicitly says that space is the province of all mankind. implying that its benefits should be shared. But how do we ensure that happens? Without clear, modernized international frameworks, the scramble for space resources could lead to conflicts, a tragic repeat of the terrestrial colonialism and resource wars that have plagued human history. This forces us to confront a critical choice about the future we want to build. Will the exploitation of space resources lead to a new era of cutthroat competition, where powerful nations and corporations carve up the solar system for their own profit, creating a vast inequality between spacefaring haves and Earth-bound have-nots? Or could it become the greatest catalyst for international cooperation we have ever seen? The immense cost and risk of developing this technology might necessitate global partnerships, leading to shared infrastructure and agreed-upon rules for fair and sustainable extraction. We have a unique opportunity to learn from the mistakes we've made on Earth. We can choose to implement principles of sustainability from the very beginning, mandating responsible mining practices that preserve the scientific value of these pristine worlds and avoid the environmental catastrophes of terrestrial extraction. The question of ownership and equity isn't just a legal technicality. It's a philosophical one that gets to the very heart of why we explore. Is it for the benefit of a few or for the advancement of all humanity? The path we choose will set a precedent for centuries to come, defining whether our expansion into the solar system is a story of division or one of our species' greatest unifying achievements. The sheer scale of the cosmos presents us with the ultimate engineering challenge. Proxima Centauri, our very next-door stellar neighbor, is not just a short hop away, it's a staggering 4.24 light-years into the void. To put that in perspective, if you could board a spacecraft traveling as fast as the Voyager 1 probe, which is hurtling away from us at over 38,000 miles per hour, your journey to this nearby star would still take over 70,000 years. You would be long gone before the voyage had even truly begun. This is the fundamental barrier of interstellar travel, the incomprehensible distances involved, coupled with the universe's strict speed limit, the speed of light. It means that reaching another star within a single human lifetime isn't just difficult. It feels almost like a violation of the laws of physics as we understand them. Yet the human spirit is not so easily deterred by vast emptiness. We have already begun to dream up and even sketch out on paper concepts that could one day turn this dream into a reality. One of the most audacious and surprisingly plausible ideas is known as nuclear pulse propulsion, a concept studied in the 1950s and 60s under the name Project Orion. The idea was as terrifying as it was brilliant. The spacecraft would literally drop small nuclear bombs out of its rear and then detonate them. A massive, heavily shielded pusher plate at the back would absorb the tremendous force of each explosion, riding the blast wave like a surfboard on a wave of fire. Each detonation would provide a powerful kick, accelerating the ship forward. In theory, an Orion-type ship could reach a significant fraction of the speed of light, cutting the travel time to nearby stars down to a few centuries. While the political and environmental implications of launching such a vessel from Earth are obviously prohibitive, the sheer raw power of the concept proves that the energy for interstellar travel does exist. We just need to find a way to harness it safely. A more elegant and perhaps more feasible solution for a very small probe is the concept of a light sail, championed by initiatives like Breakthrough Starshot. This visionary plan involves constructing a vast array of powerful ground-based lasers. Their light would be focused on an incredibly thin, reflective sail attached to a tiny, gram-weight spacecraft no larger than a computer chip. The constant pressure from all those photons striking the sail would, over time, push the tiny probe to velocities approaching 20% the speed of light. At that pace, it would reach the Proxima Centauri system in just about 20 years and could then beam back images and data, a process that would take another 4.24 years to reach us. The engineering challenges are monumental, building the laser array, perfecting the sail material, and ensuring the tiny probe can survive the intense radiation and micrometeorite impacts of interstellar space. But unlike theories that require new physics, Starshot is based on principles we already know to be true. Then there are the concepts that truly push at the boundaries of known science, the ones that promise to bend the rules of the universe itself. The most famous of these is the warp drive, popularized by science fiction but given a tantalizing hint of mathematical respectability by physicist Miguel Alcubierre in the 1990s. The Alcubierre drive doesn't propose moving faster than light through space. Instead, it suggests a way to manipulate space-time itself. Imagine contracting the space in front of a spacecraft while simultaneously expanding the space behind it. The ship would then sit inside a stable bubble of flat space-time, a warp bubble, and would be carried along as the bubble itself moves faster than light. It's like a surfer on a wave. The surfer isn't moving through the water, the wave is carrying them. The catch, and it's a colossal one, is that this model requires the existence of exotic matter with negative energy density to create and sustain the warp bubble. Whether such matter exists or can be created is one of the biggest unanswered questions in physics, making the warp drive a beautiful dream for now, but a dream that keeps theoretical physicists endlessly fascinated. If we cannot cheat physics to get there quickly, then we are forced to confront the daunting prospect of long-duration voyages, journeys that would span generations. This is the realm of the generation ship, a self-contained ark carrying a human population large enough to maintain genetic diversity and a fully functional society. This vessel would have to be a perfect closed-loop ecosystem, recycling every single atom of air, water, and waste. Its inhabitants would live their entire lives aboard, knowing that only their distant descendants would ever set foot on a new world. The social and psychological challenges of such an endeavor are almost beyond imagining. How do you maintain purpose and cultural stability over centuries of isolation in the dark? What happens if the society aboard fractures or forgets its mission? The ethical dilemma is equally profound. Is it right to commit countless generations to a life of confinement in the void, all for a goal they did not choose? An alternative to keeping everyone awake is to put them to sleep. Suspended animation or cryogenic hibernation is a staple of science fiction that has some basis in real-world medical science. Doctors already use therapeutic hypothermia to slow a patient's metabolism during complex surgeries. Researchers are actively studying the mechanisms of hibernation in animals like bears and Arctic ground squirrels, hoping to one day induce a similar torpor state in humans. On an interstellar voyage, crews could cycle through periods of hibernation, waking only for brief periods to check systems before returning to sleep. This would solve the problem of generational drift and psychological strain, but it introduces immense medical risk. What are the long-term effects of suspended animation on the human brain and body? A technical failure in the life support systems for a sleeping crew would be a silent, total catastrophe. Each of these concepts, from brute force nuclear propulsion to delicate light sails and speculative warp bubbles, represents a different bet on the future of physics and human ingenuity. They ask us not just if we can build a machine, but what kind of civilization we aspire to be, one that sends out tiny robotic scouts, one that builds arks for a long pilgrimage, or one that learns to fold the very stars to its will. This challenge is the ultimate expression of our curiosity, a testament to the fact that some horizons are so compelling that we will spend centuries, and perhaps even millennia, striving to reach them. And so, after contemplating the immense engineering and profound philosophical challenges of reaching for the stars, we arrive at a humbling and thrilling truth. For all our theories and all our ambitions, the universe almost certainly holds wonders we haven't even begun to imagine. Our current map of reality, from quarks to the cosmic web, is likely a small island in a vast ocean of the unknown, and the shoreline is constantly being redrawn by new discoveries that defy our existing explanations. This isn't a failure of science. It is its very essence, the recognition that every answer uncovers deeper, more fascinating questions. Consider the deeply puzzling anomaly known as dark flow. By meticulously mapping the cosmic microwave background, the afterglow of the Big Bang, astronomers have detected a strange and unexpected motion. Huge clusters of galaxies, on a scale of billions of light-years, seem to be drifting in a particular, coordinated direction at astonishing speeds that cannot be explained by the known gravitational forces in the observable universe. It's as if these immense structures are being gently tugged by something immense lying far beyond the horizon of what we can see. One provocative explanation is that this gravitational influence is coming from a region of space-time that is causally disconnected from our own, perhaps a consequence of the gravitational pull from another universe in a vast multiverse. While this remains highly speculative, dark flow stands as a stark reminder that our cosmic neighborhood might be much larger and far stranger than our standard models allow. Then there are the cosmic fireworks that continue to baffle us. While we've made great strides in understanding the origins of most gamma-ray bursts, the most energetic explosions in the universe, a small subset stubbornly refuse to fit into our neat categories. Some bursts release energy in patterns or with intensities that don't neatly align with the collapse of a massive star or the merger of two neutron stars, the two leading theories. Could these outliers be the signature of something even more exotic and violent? Perhaps the collapse of a hypothetical boson star, the eruption of a supernova from a primordial star made of pure hydrogen and helium that was hundreds of times more massive than our Sun, or even the distant echo of cosmic strings, theoretical, one-dimensional defects in the fabric of space-time left over from the Big Bang, vibrating and snapping to release unimaginable energy. Each unexplained flash is a clue pointing toward physics operating under conditions so extreme we cannot yet replicate them in any laboratory. The history of astronomy teaches us a powerful lesson in humility and anticipation. Every time we have built a new kind of eye to look at the cosmos, we have been utterly surprised. The discovery of pulsars in the 1960s was completely unexpected. Their perfectly regular radio pulses were so artificial-looking that the team that found them half-jokingly labeled the signal LGM-1 for Little Green Men. Before the 1990s, we didn't know for certain if planets existed around other stars. Now we know of thousands, and the sheer diversity of these exoplanets, from puffy hot Jupiters to diamond planets, has demolished our simple, solar system-centric view of how planetary systems form. This pattern tells us that the greatest discoveries are often the ones we didn't think to look for. This is why the launch of telescopes like the James Webb is so electrifying. It is not just a tool for answering the questions we already have. It is an engine for generating new, more profound mysteries. By peering into the atmospheres of distant exoplanets with unprecedented precision, it might detect a bizarre chemical imbalance that points to a form of life with a completely different biochemistry than our own. By gazing at the very first galaxies, it could reveal patterns of structure formation that force us to completely rewrite the story of cosmic dawn, perhaps hinting at the influence of unknown dark matter interactions or primordial forces that faded away shortly after the Big Bang. The most exciting possibility is that its most significant finding will be something no theorist ever predicted, a signal or an object that is currently absent from every astronomy textbook and every scientific model. This relentless, thrilling pursuit of the unknown is what truly defines the scientific adventure. It is a process of perpetual wonder, where the destination is not a final answer but a deeper appreciation for the magnificent complexity and sheer strangeness of the cosmos. It underscores the most important lesson of all, that the universe is not only stranger than we suppose, but stranger than we can suppose. This acceptance of the unknown, this eager anticipation for the next great surprise, is what propels us forward, ensuring that our journey of cosmic discovery will never truly end. This journey through the cosmos inevitably brings us to a humbling and profound crossroads, where we must confront not just the mysteries of the universe, but the very limits of our own ability to understand them. We are, after all, a species that evolved to recognize patterns on the African savanna, to avoid predators and find food. Our brains are magnificent, but they are not necessarily wired to intuitively grasp the true nature of reality at its most fundamental levels. We build complex tools and mathematics to extend our perception, but we may eventually hit a wall, a point where certain truths are simply beyond the reach of any possible intelligence confined within our particular universe. This isn't just philosophical speculation, it's a conclusion suggested by some of the most important discoveries in 20th century science and mathematics. In the strange world of the quantum, we find Heisenberg's uncertainty principle, which tells us that there is a fundamental trade-off in what we can know. We cannot precisely measure both the position and the momentum of a particle at the same time. The more accurately we pin down one, the more fuzzy and uncertain the other becomes. This isn't a limitation of our instruments, it's a built-in feature of reality itself. It's as if the universe imposes a fundamental resolution limit, a cosmic pixelation that prevents us from seeing everything with perfect clarity all at once. This inherent fuzziness means that at the most basic level, the universe may be probabilistic, not deterministic, and that there are aspects of it that are forever hidden from direct observation. At the same time, in the abstract realm of pure logic, the mathematician Kurt Gödel delivered another stunning blow to our dreams of omniscience. His incompleteness theorems proved that within any sufficiently complex mathematical system, there will always be true statements that cannot be proven to be true using the rules of that system. In other words, mathematics, the very language we use to describe the universe, contains within it truths that are unprovable. There will always be gaps, statements that we can see are true but can never logically derive from the axioms we started with. This suggests that even in the pristine world of logic, a complete and final theory of everything might be a mathematical impossibility. Our description of the cosmos may always be, in some sense, incomplete. These are not temporary barriers waiting for a smarter scientist or a more powerful computer. They appear to be absolute, fundamental limits woven into the fabric of logic and reality. So, what does this mean for our quest? Are there cosmic mysteries that will forever remain just beyond the edge of our understanding, eternally shrouded in shadow? Could the ultimate nature of dark energy or the question of what preceded the Big Bang be forever unknowable, not because they are too distant, but because the answers lie outside the conceptual framework of any possible universe that contains beings like us? This might sound discouraging, but in truth, this recognition is one of the most mature and empowering insights of science. It instills a necessary humility, a reminder that we are participants in a grand, unfolding story, not its omniscient authors. It means the well of discovery may never run dry. every answered question doesn't lead to a final endpoint, but to a new and more fascinating horizon of inquiry. This humility is what separates science from dogma. It is a process of endless questioning, not a possession of final answers. It acknowledges our small place in the grand scheme while simultaneously celebrating the incredible power of our curiosity to take us as far as it possibly can. This beautiful, endless dance with the unknown, this drive to press right up against the boundaries of knowledge, is perhaps the most defining and noble trait of our species. And it is a dance we must ensure continues long after we are gone, by passing the torch of wonder to those who will carry it into the future. That spark of wonder ignited by a starry night sky is one of the most powerful forces we have for shaping the future. It's that moment of awe, that profound curiosity about the cosmos, that has guided countless young minds toward a lifetime of discovery in science, technology, engineering, and math. This isn't just about filling classrooms, it's about nurturing the very individuals who will one day solve the mysteries we've been exploring together. They are the future engineers who will design the spacecraft for interstellar travel, the physicists who will unravel the nature of dark matter, and the biologists who might be the first to identify life on another world. Our ability to inspire them today directly fuels the breakthroughs of tomorrow. Making this inspiration accessible is more crucial than ever, and we've moved far beyond the traditional textbook. Today's generation is being captivated by breathtaking documentaries that bring the beauty of nebulae and the drama of rocket launches right into their living rooms. Social media platforms allow astronauts to broadcast their daily lives from the International Space Station, sharing videos of floating in microgravity and offering a truly personal connection to space exploration. Museums and planetariums create immersive, hands-on exhibits that make complex concepts tangible, and programs like NASA internships and student competitions provide real-world experience, placing young people directly into the heart of the mission, whether it's analyzing data from a Mars rover or helping to write code for a satellite. These initiatives demystify the path to a STEM career, showing that it's not an unreachable dream but an exciting and attainable journey. Central to this journey are the role models who light the way. When a child sees someone who looks like them, whether it's an astronaut like Jessica Watkins conducting science in orbit, an engineer like Diana Trujillo leading the team behind a Mars rover, or a visionary like Elon Musk championing ambitious space projects, it sends a powerful message: this field is for you. These individuals are living proof that curiosity, coupled with perseverance, can lead to extraordinary achievements. Their stories are not just about triumph, but also about overcoming setbacks and failures, demonstrating that resilience is just as important as brilliance in the quest to understand the universe. This leads us to a vital question: how do we ensure that this sense of excitement and opportunity reaches everyone? Making space science truly inclusive means actively working to break down barriers. It means creating outreach programs that serve under-resourced communities, providing scholarships and mentorships to students from all backgrounds, and ensuring that educational materials are available in multiple languages and accessible formats. Diversity is not a box to be checked, it is our greatest strategic advantage. When we bring together people with different life experiences, cultural perspectives, and ways of thinking, we foster a richer, more creative environment for problem solving. The next great idea for clean energy might come from a student in a rural community, and the algorithm that helps us decipher signals from distant stars might be written by a coder from a bustling metropolis halfway across the globe. By investing in education and embracing a wide spectrum of talent, we are not just building a pipeline of scientists and engineers. we are ensuring that the Chronicles of Celestial Wonders will continue to be written with fresh ink, new voices, and boundless imagination for generations to come. This relentless drive to explore is etched into the very core of our species, a legacy written in the bones of ancient navigators who set sail for unseen horizons and the astronauts who now leave our planet's embrace. It is a story that stretches from the first human who wandered beyond a familiar valley to the teams preparing for a journey to Mars, a narrative of constant motion powered by an insatiable need to see what lies just beyond the next hill, the next ocean, the next world. This spirit is far more than mere wanderlust. It is the ultimate expression of optimism, a profound belief that the unknown holds not just danger but promise. It is a testament to our resilience, our ability to face down immense challenges, to learn from catastrophic failures, and to persevere with a focus fixed firmly on the horizon. This intrinsic drive suggests that for humanity, the act of discovery is as essential as breathing, a fundamental part of what makes us who we are. What is truly remarkable is how this deeply personal urge translates into our greatest collective achievements. Space exploration, in particular, has a unique power to dissolve the artificial borders that divide us on Earth, uniting people across nations and cultures in a shared, awe-inspiring endeavor. When we watch a rocket launch or see a new image from a distant world, we aren't watching as Americans or Russians, Europeans or Asians. We are watching as Earthlings, sharing a moment of collective pride and wonder. This perspective is perhaps the most valuable gift space exploration has given us, the ability to see our planet not as a collection of separate countries, but as a single, fragile, beautiful oasis of life floating in a vast and inhospitable cosmic ocean. It fosters a sense of global citizenship and a shared responsibility for our common home, reminding us that despite all our differences, we are all crew members on the same small spaceship, hurtling through the void together. So what is the engine behind this incredible drive? The motivation is a powerful mixture of profound, interconnected desires. There is, first, the deep-seated desire to understand our own origins. We look to the stars to answer the most fundamental questions. Where did we come from? How did the universe begin? Are we alone? By studying other planets, we learn more about Earth's own history and its future. By searching for life elsewhere, we seek to understand the very nature of life itself. Alongside this quest for understanding is the powerful instinct to ensure our long-term survival. Establishing a presence on other worlds is the ultimate insurance policy, a way to safeguard the human species and the biosphere's genetic heritage against planetary-scale catastrophes that could occur here on Earth. And underpinning it all is a simple, pure, and irresistible curiosity, the innate human urge to know, to see, and to experience that which is new and mysterious. It is the same spark of wonder that lights up a child's eyes when they see a shooting star, now amplified by the tools of science and the power of rockets. This brings our epic journey through the Chronicles of Celestial Wonders full circle, right back to where we began, under the canopy of a starry night sky, filled with that same primal sense of awe. We have ventured from the invisible realms of dark matter to the event horizons of black holes, from the possibility of life on ocean worlds to the mind-bending concepts of multiverses and simulations. We have seen how every mystery solved unveils two new ones, a beautiful and unending cascade of questions that ensures the adventure of discovery will never be complete. This reflection isn't an ending, but an invitation, a reminder that the cosmos is not a distant, separate entity, but a part of us, and we are a part of it. Every time we choose to look up and ask why, we are participating in the greatest story ever told, a story that continues to unfold with each new observation, each new mission, and each new generation that dares to dream of the stars. And so our grand tour of the cosmos draws to a close, but the journey itself is far from over. We have ventured together from the incomprehensible, invisible dominance of dark matter and dark energy, which together shape the fate of everything we see, to the mind-bending realities of black holes, where the very laws of physics break down at the point of a singularity. We have felt the ripples in space-time from colliding neutron stars and listened for the whispers of intelligent life in the vast, silent expanse between stars. We have pondered the fine-tuning of our universe and the tantalizing possibility that we are but one bubble in an infinite, frothing multiverse. Each mystery we've uncovered has not been a final destination, but a doorway, an invitation to step through and ask the next, even more profound question. This endless cycle of discovery is the true heartbeat of science. It's a process that thrives not on having all the answers, but on nurturing a relentless, childlike curiosity. The moment we stop questioning, the moment we decide we have it all figured out, is the moment the adventure truly ends. The cosmos is not a puzzle to be solved, but a story to be continually read, with each chapter revealing a plot twist more astonishing than the last. The unknown is not something to be feared, but to be embraced as the source of all wonder and the fuel for all exploration. It is this very state of not knowing that drives us to build bigger telescopes, to send robotic explorers to distant moons, and to dream of one day walking on other worlds. This sense of wonder is our shared inheritance. It belongs to every single one of us, regardless of background or expertise. You don't need a degree in astrophysics to step outside on a clear night, look up, and feel that profound connection to the universe. That feeling of awe is the starting point for everything. It's the spark that ignites a lifelong passion for learning. We encourage you to nurture that spark. Follow your curiosity wherever it leads you, whether that's delving into a documentary, reading an article about a new exoplanet discovery, or simply taking a few moments each week to gaze at the stars and let your imagination roam. The cosmos is the grandest story ever told, and you have a front row seat. We would love to hear which of these cosmic mysteries captured your imagination the most. Did the enigma of dark energy leave you pondering the ultimate fate of everything? Were you drawn to the search for life on the icy moons of Jupiter and Saturn? Or did the philosophical implications of the simulation hypothesis really make you think? Share your thoughts and questions in the comments below. Let's continue this conversation together as a community of curious explorers. If you want to join us on the next adventure into the unknown, make sure to subscribe and hit the notification bell so you don't miss out. There are always new wonders to uncover, and we can't wait to explore them with you. Never stop looking up and never stop wondering.